Thousands of planes, just sitting in the desert. They'll never fly again. But each one? Millions of dollars being carefully stripped away, bolt by bolt, right now. One engine, 30 million. Business class seats, a few thousand each. Even the coffee maker from an old Boeing gets auctioned off. People think aircraft boneyards are graveyards. But the truth is, they're the most profitable recycling operations on the planet. Today, we're going where almost no one gets to go. To watch a 150-ton giant get torn down to scrap metal in 30 minutes. And why this isn't the end at all. It's a whole new beginning. Why the desert? That's the first question that pops up when you see these thousands of acres packed with planes. It's pushing 100 degrees Fahrenheit out here, and the humidity's basically zero. Perfect conditions to keep metal from rotting and rusting. Planes can sit here for decades and still look like they rolled off the tarmac at JFK yesterday. But not all of them are here to die. A lot are just waiting for better times. The airplane recycling process starts with what the pros call harvesting. This is the most profitable part of the job. When an airline decides a plane is no longer flight-worthy, engines are the first things to go. One of those engines can run anywhere from $10 to $30 million in working condition. They're pulled using special lifts and shipped off for diagnostics. Even if the airframe itself is old, those engines can keep flying on other aircraft for years to come. It's like a heart that keeps beating in another body. Besides the engines, they remove the auxiliary power unit. That's a small engine in the tail of the plane that provides electricity when the main motors are shut down. That thing's worth serious money too. Next, we step inside the cockpit. For aviation fans, this is like Aladdin's cave. There are hundreds of switches, screens, and computers. Each black box or navigation instrument can fetch several thousand or even tens of thousands of dollars on the secondary market. Workers remove all the equipment very carefully, pack it into special anti-static boxes, and send it for testing. Same goes for the passenger cabin. You'd be surprised, but even the seats have value. A set of business class seats can be sold for several $1,000s to private companies or movie studios building sets. Galleys, meal carts, even coffee makers, everything goes up for sale. There's nothing worthless on a plane until it's just an empty metal tube. Once everything valuable is stripped out, the environmental specialists step in. An aircraft is a complex machine packed with hazardous fluids. Every last drop has to be drained. The fuel tanks of a large plane can still hold several hundred gallons of kerosene that can't be pumped out during normal operations. Hydraulic fluid also needs draining. It's highly toxic, along with lubricant from all the mechanisms and antifreeze. Just imagine, the total volume of all these technical fluids can reach 500 gallons. All of it gets drained into special tanks for proper disposal. Workers also remove batteries, fire extinguishers, and oxygen cylinders. If even one of those cylinders stays inside when the heavy machinery moves in, it can explode with the force of an artillery shell. When the plane becomes completely clean, the most spectacular part begins, destroying the fuselage. Here we see a giant excavator at work, but instead of a bucket, it's equipped with hydraulic shears. They're sometimes called the guillotine. The operator of this machine is a true master. He drives up to the aircraft and starts chomping off pieces of the wings. The sound is like someone tearing open a giant soda can, only 1,000,000 times louder. The metal crunches, cracks, and gives way under pressure of several thousand pounds per square inch. First they cut off the wings, then the tail section. All of this is done according to a specific plan, so the structure doesn't collapse onto the machine itself. Next, the excavator tackles the fuselage. It simply slices this massive steel tube into chunks about 20 feet long. This is done so these pieces can be loaded onto regular trucks and hauled to the metal mill. Watching what was once a majestic airliner that flew at 30,000 feet get turned into a heap of mangled metal in 30 minutes. It's a sight that makes you think about how fleeting time really is. But the equipment operators don't have time for philosophy. They need to sort the scrap as fast as possible. Sorting is the key to profit in this business. An aircraft is made up of different metals, and they can't be mixed. About 80% of the weight is aluminum, but it also comes in different grades. The skin is one alloy. The structural beams inside are another. There's also titanium, which is used in high-temperature areas, like near the engines. Titanium costs several times more than aluminum, so there's a real hunt for every piece of this metal. There's also steel in the landing gear, and some copper in those leftover wires that couldn't be pulled out by hand. Workers use magnets and special scanners to separate these piles of metal. A lot of people think aircraft scrap is the end of the story, but it's actually the beginning. The aluminum from these planes, it's the highest quality metal. They melt it down at around 1200 degrees Fahrenheit and make new ingots. From that aluminum, they can then make just about anything. Beer cans, parts for new cars, or even new aircraft. It's a closed loop where nothing goes to waste. Experts say roughly 95% of a modern passenger jet's weight can be recycled and used again. That's an incredible number for such complex machinery. Here's a fun fact for those who love numbers. In 1 year at a boneyard like this, they can completely dismantle up to 200 aircraft. If you take the average weight of each at 150,000 pounds, that's 30 million pounds of metal going back into the economy. This is a billion-dollar business, and it's only growing because airlines are trying to upgrade their fleets faster to more fuel-efficient models. Older planes become too expensive to maintain, so they end up right here, under the Arizona sun. There's always something a little sad about watching planes die, but at the same time, I'm blown away by how incredibly organized this whole process is. There's no chaos here. Every swing of the excavator, every step a worker takes with a wrench in hand, it's all calculated down to the second. This is a massive machine that converts the past into the future. We've just watched hydraulic power transform a symbol of technological progress into raw material for new achievements. And even though these aircraft will never take to the skies again, they live on in the things we use every day. As we walk across this yard, there's a constant crunch of broken glass and insulation debris under our feet. The air smells like hot metal and dry grass. It's a unique atmosphere that's tough to capture in words. This is where engineering genius meets inevitable destruction. But it's not destruction for destruction's sake. It's destruction for the sake of creating something new. And that's really what our civilization is all about. We're constantly recycling the old to build something better, faster, and more efficient. I hope you enjoyed peeking behind the fence of this aircraft graveyard with me. Now, next time you're flying off on vacation, you'll know what awaits your plane in 20 or 30 years. And it's not scary at all. It's just another chapter in the life of metal and technology. Thanks for watching my explorations. Hit that like button if you're into massive machinery like this, and subscribe so you don't miss new journeys to the most fascinating places on our planet. We'll find plenty more spots where metal tells us its incredible stories. See you in the next video, where we'll tear apart something just as epic. Bye! In a world where every second counts, water produces over 50% of all clean energy on the planet. But have you ever wondered what price nature pays for this power? To build one hydroelectric plant, you need more concrete than for 10 skyscrapers. And the river has to be stopped. Its flow gets diverted into a tunnel. The riverbed gets dried out, and a foundation is poured that can withstand the pressure of thousands of tons of water. But behind every such structure lies not just engineering, but also mystery. By the end of this video, you'll discover how water becomes electricity that powers entire cities, and what dangerous price humanity pays for controlling a river. A hydroelectric power plant is where water transforms into electricity. The river's flow gets directed through turbines that spin and generate electrical power. It's a clean energy source with zero carbon emissions, and it works 24/7. But to make this possible, you need to build a dam, a massive structure that holds back the river, creates a reservoir, and controls water flow. The first and most crucial stage of hydroelectric plant construction is site selection. Engineers carefully study the terrain, geology, and hydrology of the region, looking for a narrow section of river with solid, stable banks. The ideal option is a natural gorge between mountains, where water already has significant elevation drop. This reduces the amount of earthwork needed and ensures powerful water pressure on the turbines. At the same time, it's important to have populated areas nearby that need a stable electricity source. The closer to the consumer, the lower the transmission losses. Such location also simplifies construction logistics, material delivery, equipment operation, worker housing. Site selection is a balance between natural conditions, technical capabilities, and human needs. This is where the foundation of future energy infrastructure gets laid. Before starting hydroelectric plant construction, you need to tame the river itself. Its flow gets temporarily redirected into a specially created bypass channel, or tunnel that's built alongside the future dam. This is a complex engineering operation that allows drying out the section where the main structure will be built. Working in the dry is critically important. Concrete work, rebar installation, and foundation work are impossible underwater. Such a river bypass can function for several months or even years while construction continues. After completing the main work, water gets returned to its new channel, now through turbines that start producing electricity. Once the river is diverted, builders move on to preparing the base, the foundation of the future dam. First, they carefully level the ground, remove unstable rock formations, compact the soil, and reinforce it with special materials. Then, concreting begins. They pour thousands of cubic meters of reinforced concrete, layer by layer, creating a monolithic structure. This foundation must be incredibly strong. It withstands not only the massive water pressure, but also possible earthquakes, seasonal water level fluctuations, and decades of operation. A mistake at this stage means disaster risk, so quality control here is maximum. They use laser levels, geodetic sensors, and every batch of concrete undergoes laboratory testing. From this very foundation grows the giant wall that changes the landscape and energy map of the region. The type of construction depends on local terrain and river characteristics. If the banks are solid and located close to each other, they choose an arch dam that transfers water pressure to the side rocks. If the river is wide and the terrain is flat, they build a gravity wall that holds back water with its own weight. In any case, it's a gigantic structure. Height can reach 984 feet, and length can span several hundred yards. For its construction, they use tens of thousands of tons of concrete, delivered by conveyors, mixers, and sometimes even cable cars. Work continues for years, often non-stop, day and night. Hundreds of people work on site: concrete workers, welders, surveyors, installers. Every stage requires precise coordination because a mistake can cost millions. The key stage of converting water into electricity happens in the lower part of the dam, where hydro turbines are installed. These are massive metal structures with blades resembling giant fans. When water from the reservoir gets directed downward under high pressure, it passes through the turbines, forcing them to rotate. This motion transfers to generators, devices that convert mechanical energy into electrical energy. A generator consists of a rotor and stator. When the rotor spins, electric current emerges in the magnetic field. All this happens with incredible precision. Even a small balance disruption can stop the system. To ensure stable operation, turbines get regularly serviced, cleaned of sediment, and temperature monitored. The result is powerful electricity that enters the grid and powers cities, factories, schools. Right here, in the depths of the concrete wall, the energy that drives the modern world is born. When all main structures are completed — foundation, dam wall, turbines, and generators — comes the moment of returning the river to its new channel. Engineers block the bypass canal, and water again gets directed toward the dam, but now in a controlled manner. It begins gradually filling the reservoir that formed behind the concrete wall. This process isn't quick. To avoid sudden level changes that could damage the structure or cause landslides, filling happens in stages. Sometimes this takes weeks or even months. Meanwhile, they monitor bank conditions, water levels, wall pressure, and turbine operation. When the reservoir reaches optimal level, the hydroelectric plant enters normal operation. It starts steadily producing electricity that enters the grid. To build one dam, they use enough material to construct 10 modern skyscrapers. This isn't an exaggeration. Concrete gets poured in layers, day and night, thousands of tons at a time. It's delivered by conveyors, mixers, barges, sometimes even cable cars. Such volume is needed to create a monolithic wall capable of restraining a river. But concrete is only part of the story. Water held back by the dam exerts colossal pressure. On every square foot of wall, dozens of tons of force. It's like several trucks pressing simultaneously on a door-sized area. Such pressure doesn't just affect the structure, but also creates potential for energy production. The greater the water drop height, the more energy can be obtained. Water flow gets directed through turbines that spin and drive generators. All this without burning fuel, without emissions, just nature's force. One large hydroelectric plant can provide electricity to millions of people. That's schools, hospitals, factories, neighborhoods, entire cities. In some countries, hydropower is the main electricity source, stable and ecological. When they build a dam, the river stops flowing freely. It gets restrained, redirected, accumulated. This changes the landscape. Valleys, forests, fields get flooded. Dozens of square miles of territory where people once lived, trees grew, and animals ran can end up underwater. Sometimes entire villages need relocation. Roads, bridges, and cemeteries need moving. It's a painful process requiring social support, compensation, and careful planning. At the same time, the river's life changes. Water flow becomes controlled, affecting fish accustomed to seasonal migrations. For example, salmon or sturgeon can lose access to spawning grounds if special fish passages aren't provided. Channels or ladders that fish can use to bypass the dam. Without them, populations decrease and sometimes disappear completely. Water's chemical composition also changes, along with its temperature and oxygen levels. In reservoirs, water stagnates, which can cause algae blooms or death of some species. The region's microclimate changes. It becomes more humid, fog appears, wind patterns shift. That's why modern projects try to minimize ecological damage. Engineers work together with ecologists, hydrobiologists, and geographers. They create fish passages, plant new forests, relocate rare species, and form artificial islands for birds. In some cases, they even create new ecosystems, wetlands and floodplains that compensate for losses. A hydroelectric plant is a powerful source of clean energy, but it shouldn't be a source of destruction. Balance between technical progress and nature is the main challenge of the 21st century. And this is where new construction ethics are born, not just to build, but to preserve. Every nuclear reactor on the planet has an emergency brake. Not a button, not a switch. A metal. Drop it into the core, and the chain reaction stops cold. Pull it out too slowly, and you get Chernobyl. The entire world produces just 70 tons of this metal per year. That's one railroad car. One single car, standing between controlled fission and catastrophe. 5 factories make it. Maybe 6, if you count one in China that nobody talks about openly. Fewer factories than NFL teams. And here's the thing, this same metal is sitting inside your phone right now. Billions of devices, atoms-thin layers. The metal is called hafnium, and nobody told you about it. But before hafnium ends up in a reactor or a chip, it has to be ripped from its chemical twin. That separation is one of the hardest jobs in metallurgy. Hafnium never shows up alone. Nowhere on Earth. Never has. It hides inside zirconium. Every sample of zircon mineral ever pulled from the ground has 1 to 3% hafnium baked into it. Always. No exceptions. Now pay attention to this. Zirconium and hafnium are chemical twins. Same atom size. Same valence. Same behavior in almost every reaction you throw at them. So alike that Mendeleev never spotted hafnium when he built the periodic table. It stayed hidden for over 50 years, until 1922, riding on zirconium's back like a stowaway. Think about that. An element hiding in plain sight for half a century. Separating these two costs a fortune. Not because the chemistry is exotic, because the difference between them is almost nothing. So why bother? One property. One single property where they're total opposites. And that property keeps nuclear reactors from melting down. Zirconium is transparent to neutrons. They fly straight through it like light through glass. That's why nuclear fuel rods are wrapped in zirconium. Hafnium does the exact opposite. It swallows neutrons, 600 times more than zirconium. 600. That makes hafnium the emergency brake of every nuclear reactor. Control rods, the metal plates that slide into the core to kill the chain reaction, made from hafnium. When something goes wrong, hafnium rods drop in. They absorb every neutron in their path. Reaction over. American nuclear submarines run on hafnium control rods. Compact, reliable, no second chances needed. Now here's where the money starts burning. To make nuclear-grade zirconium, every trace of hafnium must come out. To get pure hafnium, it has to be stripped from the zirconium completely. Both processes happen at the same plant. Both are brutal. Both start with sand, a specific mineral pulled from beaches in Australia and Africa. What happens next involves 100 repetitions of the same chemical trick and a column of machines taller than a 3-story building. Raw material, zircon sand. Looks ordinary. Slightly heavier than beach sand. Faint metallic shimmer. It gets processed into zirconium chloride, a powder that acts like salt with an attitude. Sucks moisture from the air so aggressively that workers handle it in climate-controlled dry rooms. The hardest part comes next. Liquid-liquid extraction. Dissolve that chloride in water. Add an organic solvent. The two liquids grab zirconium and hafnium at slightly different rates. Hafnium moves a tiny bit more into the organic layer. Zirconium stays in the water. A tiny bit. That's the problem. One pass does almost nothing, so they repeat it. 50 times. Sometimes 100. 50 separate extraction vessels chained together in a column the size of a warehouse wall. Liquid cycling back and forth for months. The electricity bill alone would make your eyes water. A single solvent leak shuts the whole line down for a week. Picture a 100-step coin sort where heads and tails are almost the same weight. That's what this machine does. And it never stops. After 100 cycles, hafnium comes out as a chloride compound. Still not metal. Turning it into metal requires temperatures that would melt most equipment. Hafnium chloride gets packed into a sealed vessel with chunks of magnesium. Temperature climbs to 1650 degrees Fahrenheit. Magnesium rips the chlorine atoms off hafnium and bonds with them. What's left behind is pure hafnium. But it comes out as a rough, grey, porous mass. They call it hafnium sponge. Looks like pumice stone someone left in a furnace. Pick it up and it feels heavier than it should. That ugly grey sponge costs over $1,000 per kilogram. More per ounce than gold at certain market points. And it's still not ready for a reactor. Only a handful of companies buy it directly. Framatome in France, Westinghouse in the US. Shipments move in sealed containers under strict tracking. Lose a batch in transit, and people in government offices start asking questions. Vacuum arc furnace. Temperature, above 4,000 degrees Fahrenheit. Hafnium melts at 4,050. At that heat, it reacts violently with oxygen and nitrogen. Even a breath of air inside the furnace makes the metal brittle and useless. So the chamber is sealed, air pumped out, replaced with argon. No oxygen, no nitrogen, no room for error. First melt produces an ingot. Composition isn't uniform enough, so they melt it again. Sometimes a third time. The final ingot weighs 10 to 20 pounds. Gray, shiny, looks a bit like stainless steel. Think about what it took to get here. 1 ton of sand, 100 extraction cycles, a magnesium reduction at 1650 degrees, 3 passes through a vacuum furnace above 4000 degrees, all for a 20-pound bar of metal. That bar still has to prove it's clean enough. In a nuclear reactor, almost pure and pure are 2 completely different things. Nuclear-grade hafnium must contain less than 1% zirconium. Zirconium isn't toxic, it just lets neutrons pass through. If a control rod has 2% instead of 1, it absorbs fewer neutrons. Under normal conditions, nobody notices. During an emergency shutdown, when every neutron counts, that extra percent could mean the rod fails to stop the reaction in time. 1%. That's the line between safe and not safe. Every ingot gets mass spectrometry analysis. Every batch comes with a chemical passport. The buyers don't take the factory's word for it. Government nuclear programs, defense contractors. They run their own tests in independent labs. Zero trust. The cost of a bad batch isn't money. It's a reactor that won't shut down when it needs to. 5 factories on Earth can meet that standard. And now a second industry is pulling on that same tiny supply. Since 2007, hafnium has had a second life. Inside microprocessors. When transistors shrank below 12 nanometers, the old insulating layer stopped working. Too thin. Current leaked straight through like water through a cracked pipe. Hafnium oxide solved that. A few atomic layers hold the charge where silicon can't. Every modern processor contains hafnium. Phones, laptops, data centers. Microscopic amounts, but across billions of devices, it adds up. A second major buyer pulling on a supply that fills 1 railroad car per year. 1 factory down for maintenance can move global prices. 2 offline at once, and both nuclear and semiconductor start making uncomfortable phone calls. There are no hafnium mines. Not one. Every gram ever produced is a byproduct of zirconium processing. If demand for zirconium drops, hafnium supply drops with it, even if demand for hafnium is going up. 2 industries fighting over a metal that only exists because someone else needed its twin. 70 tons a year. 5 factories. A supply chain so thin that losing 2 of them would send shockwaves through nuclear energy and tech at the same time. Next time you pick up your phone, remember this. Somewhere between the glass and the battery, there are atoms of a metal that doubles as a nuclear reactor's emergency brake. And there's barely enough of it to go around. Next one. A metal they pull from volcanic rock at 3000 degrees. One country controls 90% of the supply. Today, I dragged you to a place so remote that cell service seems like technology from the distant future. And the main bosses here are massive excavators with wheels big enough to comfortably fit a small studio apartment. We're starting our journey at a nickel mine. Have you ever wondered where that perfect shine on a surgeon's scalpel comes from? Or why your pot doesn't turn into a pile of rust after cooking your first batch of borscht? The answer lies here, 1,600 feet beneath our feet. Nickel. This is the guy that makes steel tough and resistant to just about everything. But finding it? That's an adventure for the patient. Look at these numbers. To extract just 1 ton of pure nickel, miners have to move and haul to the surface about 100 tons of ore. That means the useful metal content in this rock ranges from 1 to 3%. Massive underground machines load up rock that looks like ordinary gray stone, but hidden inside is the promise of future strength. One of these dump trucks carries 240 tons of rock at a time. That's the weight of roughly 40 adult elephants, if you like those kinds of comparisons. After we've brought the ore to the surface, it's got a long journey ahead to the processing plant. There, the stone gets crushed into fine sand, washed, sifted, and turned into concentrate. It's not metal yet, but it's getting close. Then this concentrate gets shipped to a metallurgical plant. And this is where things get really interesting and really hot. We're standing inside a shop where electric arc furnaces are doing their thing. Here, temperatures climb to 3,000 degrees Fahrenheit. That's roughly 10 times hotter than your home oven when you're trying to roast that holiday duck. All this molten metal churns like fiery soup, glowing so bright that without special goggles, you really shouldn't look at it. Not if you plan on seeing anything else for the rest of your life. Into the furnace goes scrap iron, that same nickel, and one more critical player, chromium. Chromium is a whole story unto itself. For steel to officially earn the right to be called stainless, it needs at least 10.5% chromium. When this metal contacts oxygen, it forms an invisible, incredibly thin oxide film on the surface. It's so thin we can't even see it, but it becomes that impenetrable barrier that keeps the iron from oxidizing. So stainless steel doesn't rust, not because it's magical, but because it's already coated with a protective layer at the atomic level. Once the steel melts, it goes through a procedure called argon-oxygen decarburization. Sounds like the title of a PhD thesis, but the idea is pretty straightforward. Surgical steel has to be incredibly pure and contain extremely little carbon. Too much carbon? It'll buddy up with the chromium, steal it away, and the steel loses its resistance to corrosion. A mixture of gases is blown through the molten metal under immense pressure, literally burning out the excess carbon while leaving all the useful additives in place. The whole process takes about 90 minutes. You can't rush this. One mistake in the proportions, and instead of a valuable medical instrument, you get ordinary rebar that'll be covered in rust spots within a few months. Next, this fiery liquid gets poured into continuous casting machines. Steel solidifies into long, massive strips that professionals call slabs. A single slab can weigh 20 tons and stretch about 40 feet long. When they come out of the machine, they're still glowing dark red, radiating so much heat you could toast bread in a fraction of a second without even getting close. Then these slabs head to the rolling mill. Picture a giant version of a rolling pin, except instead of dough, you've got a 20-ton chunk of red-hot steel, and instead of a baker's hands, you've got massive rollers pressing down on the metal with thousands of tons of force. The metal gets run through these rollers again and again, getting thinner and longer each time. From a slab 8 inches thick, steel workers produce coils of steel ribbon just a few hundredths of an inch thick. The speed at which steel flies through these rollers in the final stages hits 40 feet per second. It looks like an actual fiery arrow racing through the plant. Now let's jump to a completely different place. Gone is the hellish heat and roar. We're at a medical instrument factory. The atmosphere here feels more like an operating room or lab, sterile, quiet, and fanatically detail-oriented. That steel ribbon we saw earlier, it's cut into small blanks. Then each blank is heated again, but now in small induction furnaces and forged in special dies. That's how the rough profile of a future clamp, forceps, or scalpel emerges. After forging, the real precision work begins. Craftsmen use grinding machines and hand finishing to perfect every curve. This is absolutely critical, because a surgical instrument must be perfectly smooth. Not a single burr or microscopic pit where bacteria could hide and multiply. The tolerances here are so tight they're measured in microns. A human hair is about 50 microns thick. We're talking about precision down to 5 or 10 microns. Once the instrument takes its final shape, it goes through heat treatment. It's heated to 2000 degrees, then rapidly cooled. This makes the steel hard, so the scalpel won't dull after the first cut, and the clamp won't bend in the doctor's hands. But after hardening, the metal becomes brittle, so it's heated again slightly, a process called tempering, to restore the necessary flexibility. One of my favorite stages is passivation. This is when the finished, already shiny instruments are immersed in baths of strong nitric acid solution. You'd think, why torture a finished product? But the acid does something really useful. It dissolves any microscopic particles of regular iron that might have gotten on the surface from the machines or the craftsman's tools. This cleaning allows that same protective chromium film we talked about at the beginning to become even thicker and stronger. After this treatment, the instrument can handle thousands of sterilization cycles in autoclaves at 273 degrees Fahrenheit under 2 atmospheres of pressure and stay shiny and clean for years. Let's crunch some numbers here, because they always help us grasp the scale of what's happening. The world produces about 50 million tons of stainless steel every year. If you stretch that metal into a thin wire, you could wrap our entire planet thousands of times. But only a tiny fraction of that steel, less than 1%, gets to become a surgical instrument. To manufacture one quality operating room set, you've got to process hundreds of tons of rock, burn through thousands of kilowatt hours of electricity, and run over 30 different quality tests. For instance, one ordinary surgical clamp passes through the hands of at least 12 different specialists, from the blacksmith to the quality controller, before it lands in its packaging. Quality control here is so strict that a tool gets scrapped even for a microscopic scratch on the surface, something the naked eye wouldn't even notice without serious magnification. And here we see the final result. A tool weighing less than 2 ounces, but packed with the labor of thousands of people, from those who descended into dark mines for nickel, to those who calibrated the lasers for marking finished products. It's a long journey, where every step is a battle for quality and purity. Subscribe to the channel so you don't miss our next deep dives, because the world of manufacturing is way more fascinating than it seems at first glance. Thanks for watching, take care of yourselves, and choose only reliable tools for your life. See you in the next video. By the way, what do you think? Will humanity ever find a metal even stronger than today's steel alloys? Or have we already hit the peak of what's possible in this field? What if I told you that a high-speed train wheel experiences temperatures hot enough to make metal glow, and still can't afford to fail? Why must this piece of steel withstand tests that would destroy any car wheel in seconds? There's a reason almost nobody suspects, and if you stay with me through to the finale, you'll discover the secret process that forces the wheel to survive where other metal simply melts. But first, tell me, does your country actually manufacture railway wheels, or are they imported? A train rockets down the tracks at over 186 miles per hour. At that speed, an ordinary wheel would simply disintegrate. Why? Because it has to withstand not just weight, but a whole series of inhuman trials. The material is everything. This isn't ordinary steel used for silverware or even car bodies. High-speed train wheels are made from a special grade of steel, melted according to a unique, meticulously refined recipe. This recipe is a combination of iron with specific alloying elements, manganese, silicon, chromium, molybdenum, that give the steel extraordinary strength, toughness, the ability to absorb impacts without failing, and endurance. Beyond that, this steel must be as pure as possible, free of any foreign impurities that could become a weak point. After the special steel is melted in massive metallurgical furnaces, it's poured into molds to create large steel billets, what we call slabs or blooms. But that's just the beginning. The real transformation starts in the forging shop. This is where one of the most powerful forging presses comes into play, along with specialized forging machines. The billet, heated until it glows bright yellow or red, that's around 2000 degrees Fahrenheit, is fed under the press. The process involves multi-stage forging. It's not a single strike, but rather a whole series of controlled pressures and rotations. The giant hammers, or jaws of the press, slowly, yet with unstoppable force, flatten and shape the red-hot metal. First stage, the billet is compressed to give it a rough circular shape, densifying the metal and eliminating internal voids. Second stage, the material is flattened and rolled, forming a disc with a central hole. This is where the future wheel's outline begins to emerge, with its rim, disc, and hub. This directional metal flow shapes its internal fibrous structure, making the wheel exceptionally strong in the required directions. Forging, unlike casting, transforms steel's microstructure. It compresses the metal's grains, eliminates casting defects, and creates a directional fibrous structure that gives the wheel exceptional strength and fatigue resistance. It's like an athlete's muscles. After training, they become stronger and more resilient. Why such complexity? Because high-speed train wheels operate under extreme conditions that are hard to imagine. When moving at speeds over 186 miles per hour, the wheel's surface heats up from friction against the rails and brake pads to nearly 2,000 degrees Fahrenheit. That's the temperature at which metal begins to glow red and change its properties. And this heating isn't constant, it's cyclical. Heating during acceleration and braking, cooling during movement. The material must withstand these constant temperature fluctuations without forming microcracks, which over time can lead to failure. Each pair of wheels carries a load of dozens of tons. A single railcar can weigh between 50 and 70 tons, and this weight is distributed across just 4 wheels, that is, 2 wheel sets. This creates constant pressure acting on the wheel. The train doesn't ride on a perfectly smooth surface. It crosses rail joints, uneven sections, and switches, which generate continuous impact loads. The wheel must be incredibly tough to absorb these shocks without cracking or breaking apart. After forging, the wheels aren't finished yet. They undergo complex heat treatment, which is key to developing their final properties. The wheel centers, the discs that connect the hub to the rim, are hardened. Hardening is a process of heating steel to high temperatures, then rapidly cooling it. This makes the metal harder and stronger. But hardening makes the metal brittle, so it's always followed by tempering, reheating to a lower temperature with slow cooling. Tempering reduces brittleness and improves toughness while maintaining high strength. This combination of hardening and tempering creates the ideal steel microstructure that can withstand extreme operating conditions. But even after all these complex processes, no wheel reaches the rails without brutal yet necessary testing. Every single wheel, without exception, undergoes ruthless inspections. Ultrasonic testing. It's like medical ultrasound diagnostics, but for metal. Special sensors send high-frequency ultrasonic waves through the wheel. If there's even a microscopic crack, void, or defect inside, the ultrasonic wave bounces off it and creates an echo that the instrument captures. This method allows us to see internal defects without destroying the wheels. A defect the thickness of a human hair is already grounds for rejection. Magnetic particle inspection. The wheel gets magnetized, then its surface is coated with fine ferromagnetic powder. If there's a crack, even one invisible to the naked eye, it distorts the magnetic field, and the powder concentrates along that crack, making it visible. This reveals even the tiniest surface defects that could become failure points during operation. Only wheels with perfect structure and 0 defects are cleared for installation on high-speed trains. This isn't engineering perfectionism. It's about the safety of thousands of passengers who trust their lives to these metal giants. While the United States isn't leading high-speed rail development like China or Japan, its rail network remains one of the world's largest, and American manufacturers have extensive experience producing high-quality wheels for various rolling stock, passenger trains, freight locomotives, and switching equipment alike. Unlike the automotive industry, where thousands of companies manufacture parts, the railroad wheel manufacturing market in the US is significantly more concentrated. This is a highly specialized field, requiring massive investments in metallurgical equipment, forging presses, and quality control systems. The two main and most powerful players in the North American railroad wheel manufacturing market are Amstead Rail and KF USA. While KF is a Spanish company, it maintains production facilities in the United States to meet local demand. Previously, other major manufacturers existed, but the market has consolidated. Total annual railroad wheel production in the US fluctuates, but can be estimated in the range of 300,000 to 500,000 units per year. This figure includes wheels for all types of rolling stock. It's worth noting that while the US can manufacture wheels capable of withstanding high speeds, The actual demand for wheels designed for continuous operation above 186 miles per hour remains relatively limited due to the scarce number of true high-speed rail lines in the country. For instance, Amtrak's Acela Express trains, running along the Northeast Corridor, reach speeds up to 150 miles per hour on certain segments, but not beyond the aforementioned threshold of 186 miles per hour, which requires specific material and design standards. However, U.S. wheel manufacturing technologies and standards do enable production that meets international requirements for high-speed trains should the need arise. From a material standpoint, American manufacturers, like their global counterparts, utilize specialized grades of carbon steel alloyed with manganese, silicon, and other elements to achieve the necessary strength, wear resistance, and toughness. Forging, heat treatment, and non-destructive testing processes are standard and comply with the highest international safety and quality benchmarks. Every year, machines are built around the world so massive and powerful that a single one could supply electricity to an entire city and costs as much as dozens of private jets. But what if I told you that inside this colossal structure, there are parts machined with precision, thinner than a human hair, and that one tiny mistake could cost millions of dollars or even destroy everything? Today we're going inside a place almost no one gets to see, the heart of turbine manufacturing. And trust me, what you're about to see will completely change how you think about engineering, if you stick around till the end. Let's start with the fact that there are two main types of these turbines, and they work on very different principles. First, the steam turbine. You'll find these at nuclear and thermal power plants, on massive tankers and icebreakers. Second, the gas turbine. It's more like a giant jet engine without wings and lives mostly at gas-fired power plants and on some military vessels. Here at the factory they make both types, but we're heading first to the steam ones because they're older, more massive, and look like they were invented 2 centuries ago. Which, actually, they were, but they're still very much around. How a steam turbine works, short and formula-free. There's a boiler that heats water into pressurized steam at anywhere from 800 to 3,000 pounds per square inch. This steam, hot, pressurized, angry, blasts through nozzles onto rotor blades. The blades start spinning. The rotor spins the shaft. The shaft spins a generator or a ship's propeller. The steam cools down, condenses back into water, and returns to the boiler. The cycle is closed. Sounds simple, but for this simple not to explode into pieces and to run for 3 years without major repairs, you need all of this around me. The first shop they take me to is the foundry. This is where every turbine begins. The casing, the outer shell that holds all the internal components under pressure, is cast from alloy steel or cast iron, depending on operating parameters. For steam turbines in large power plants, the casing is cast in 2 or 3 tiers, and each tier is a separate mold. The mass of 1/2 of a casing can reach 60 to 80 tons. The metal is melted in arc furnaces with a capacity of 50 to 150 tons of molten metal, and the temperature there is around 5,000 degrees Fahrenheit. The mold for a large casing is a pit in the floor, 6 to 10 feet deep, lined with refractory clay. The metal is poured through a system of channels, and the entire process of filling one large mold takes 15 to 30 minutes. Then the casting cools, naturally from several days to 2 weeks, depending on the mass. After cooling, the casting goes to its first inspection. Ultrasonic testing searches for voids and inclusions inside, spots where the metal didn't fuse the way it should. X-rays check critical zones. If they find something significant, the casting goes back to remelt. No compromises. The rejection rate at this stage runs 3 to 8% depending on the casting's complexity, and that's completely normal for parts this size. Next, machining. Now, here in the shop floor, there are machines that made my jaw drop. The horizontal boring mill that machines the inner casing surface. It's about 60 feet long. The table where the part sits moves. The spindle stays put. The tool freely bores the bearing and seal mounting surfaces to an accuracy of plus or minus 0.5 of an inch. Why so precise? Because the rotor spinning inside at 1500 to 3600 revolutions per minute has a clearance between its blades and the casing of 50 to 150 microinches. 1% efficiency loss at a large power plant. That's millions of dollars in extra fuel costs per year. The rotor is the star of this story. It's a shaft carrying discs with blades, and it's the most complex part of the entire turbine. The shaft for a large steam turbine is a forging made from special chromium molybdenum vanadium steel, 20 to 40 feet long and weighing 20 to 60 tons in its rough state. A forging means you take a red-hot ingot of metal and just hammer it with a press weighing 5,000 to 50,000 tons to give it the shape you need. The grain structure of the metal during forging gets oriented along the shaft's axis. That's how you achieve torsional strength. After forging, the shaft goes through heat treatment again, then heads to the machine shop. Turning takes 2 to 4 weeks of continuous work on a lathe that's nearly 70 feet long. Chips fly, coolant flows, and machining away from that massive blank reveals the sleek shaft you saw in the drawings. This is the part where I'm always amazed. A gigantic component, yet precision like a watch mechanism. Blades are a separate production line. Steam turbines at large power plants have anywhere from 8 to 20 stages, and each stage is a disc with blades. First stage blades are small, sometimes less than 2 inches tall, because the steam there is still under high pressure and dense. Last stage blades are massive, up to 5 or 6 feet long on the largest turbines. These blades are forged and milled from iron-based alloys or stainless steel, and in their final profile, they have an aerodynamic shape with precision to within plus or minus 0.02 of an inch along the entire length. Each blade is checked for resonant frequency. It can't match the operating rotational frequency of the rotor, or else after a few thousand hours, a fatigue crack will develop from vibration. How they test this is simple. They tap the blade with a small hammer and listen with a special acoustic sensor. A very elegant method for such a serious problem. Assembling the rotor. This is when it starts to feel like an operating room. Bladed discs get mounted onto the shaft using shrink fitting. The disc gets heated to 300 to 400 degrees Fahrenheit. It expands, slides onto the shaft, then cools and grips the shaft with a force no bolt could ever match. No threads, no glue, just temperature difference and precision sizing. The interference fit when cold, 1 to 3/1000 of an inch per inch of diameter. After assembly, the rotor gets balanced, and this takes 1 to 3 days. Balancing happens on a specialized rig, where the shaft spins on bearings while sensors register vibration. If there's any imbalance, metal gets removed from certain spots, or balancing inserts get installed. Allowable residual vibration on a large rotor, fractions of an ounce per inch of radius. If you think that's strict, you're thinking right. After assembly, the turbine heads to the test stand. At full operating parameters, pressure and temperature, they run the turbine for 24 to 72 hours. Sensors track bearing temperatures, vibration, steam leaks, power output. If anything goes outside the limits, stop, disassemble, analyze. There have been cases where they found a defect here that the X-ray missed initially. So the test stand isn't just a formality. It's the last line of defense before shipping. The finished turbine gets broken down into transport blocks, casing separate, rotor separate, auxiliary equipment separate. A large turbine rotor travels on a special trailer with hydraulic suspension, the kind you've seen on YouTube, with 18 axles moving at 20 miles per year. They coordinate the route a month in advance. Every bridge height and every turn width needs checking from the factory to the port or customer. Sometimes for one of these transports, they temporarily remove road signs and even take down power lines over the highway. I asked the chief engineer how many turbines they build per year. He said 12 to 20 of various types. That's it. Less than 2 per month. But each one runs for 30 to 50 years and generates electricity for hundreds of thousands of people every day. Some things don't need high-volume production. Every year, humanity produces over 360 million tons of plastic. Most of it doesn't disappear. It decomposes over hundreds of years. But what if instead of oil, we could make plastic from sugar? In the very heart of Thailand grows a crop that can change this. Sugarcane isn't just a plant, but a solar biofactory that transforms light into the material of the future. From its sweet juice is born polylactide, a bioplastic that decomposes naturally. How do they create eco-friendly packaging from simple cane that could save the planet? Watch till the end, and you'll discover the secret the industry has been keeping quiet about. Sugarcane is a true biofabricator of solar energy. It belongs to the grass family and is grown mainly in warm, humid regions, such as Thailand, Brazil, or India. In Thailand, particularly in Chiang Mai, cane occupies thousands of hectares and is a key crop for the agricultural economy. Cane isn't grown from seed. It's propagated through cuttings, pieces of stems that have nodes with buds. They're planted in prepared soil, usually in furrows, at a depth of 2 to 4 inches. After a few days, the buds sprout and new shoots begin to form. This plant is very light-loving, so plantations are located in open areas. It needs lots of water, but doesn't like stagnation, so irrigation must be moderate and regular. Over 10 to 14 months, the cane grows to 7 to 14 feet tall. Its stems are thick, juicy, filled with sweet juice. It's in this juice that sucrose is contained, the basis for sugar production. During growth, the cane actively absorbs carbon from the atmosphere, converting it into organic substances. This makes it not only a source of energy, but also a natural absorber of greenhouse gases. Sugarcane is harvested when it reaches maximum sucrose concentration, usually 10 to 14 months after planting. In Thailand, the harvest season falls during the dry period, from December through March, when the plant is no longer growing, but accumulating sweet juice. In many regions of Thailand, manual harvesting is still used. It's hard work performed by experienced workers with machetes. Before this, the plantation is often burned to remove leaves and ease access to the stems. Although this simplifies the process, burning harms the environment, so more and more farmers are switching to green cane. Harvest without fire. Large farms use mechanized combines that cut, clean, and chop the cane right in the field. This is faster, more efficient, and more ecological, though it requires investment. Important: cane residues, bagasse, aren't thrown away. They're used as biofuel, fertilizer, or even for making paper. This is an example of circular economy where nothing is wasted. After harvest, the cane must reach processing as quickly as possible. Otherwise, the sucrose level in the stems begins to drop, and that means quality loss. So logistics here is critically important. Trucks are the most common option in Thailand. Special open platforms or beds with high sides allow transporting large volumes of cane. Buggies or tractors with trailers are often used for short distances, from field to loading point. In some regions where there's appropriate infrastructure, cane is transported by rail cars. This is efficient for large volumes and long distances, but less flexible than motor transport. Water transport is a rare but possible option in areas with canals or rivers. It's used mainly for export or movement between regions. Cane is often not chopped in the field, but transported in whole stems. They're laid horizontally, densely, to minimize losses. At the factory, chopping, pressing, and juice extraction already occur. Large agricultural enterprises use automated loading systems that speed up the process and reduce losses. In smaller ones, work is still done manually or with simple mechanisms. When trucks with sugarcane arrive at the factory, the technological process begins that transforms the green plant into an innovative material, polylactide. This is a complex but fascinating journey where agricultural biomass becomes part of the ecological future. Before the cane enters processing, it's checked for sucrose content. Samples are taken from each batch to determine how suitable it is for production. Then the stems are cleaned of leaves and foreign impurities, manually or mechanically. Then our cane needs to be chopped. For this, the stems pass through mechanical crushers. These are large rollers or rotary machines with sharp blades that cut the stems into small fragments. The goal is to maximally open the cellular structure to ease juice extraction. The chopped cane is pressed in special rollers. Under high pressure, sweet juice rich in sucrose flows out. This juice is collected in reservoirs. The juice undergoes filtration to remove impurities, and then is heated for concentration. Next, a process similar to brewing kvass or yogurt is launched. Special bacteria are added that transform sugar into lactic acid. It's like when microbes turn grape juice into wine. Only here it's not alcohol that comes out, but acid. This process is called fermentation. It occurs in large tanks, bioreactors. There, everything is controlled. Temperature, acidity, how many bacteria are there? So they work properly and don't slack off. Lactic acid is the key ingredient for creating bioplastic. It has properties that allow transforming it into a polymer. The lactic acid is purified and subjected to polymerization, a chemical process in which molecules connect into long chains. The result is polylactide, a thermoplastic polymer that looks like granules or threads. These granules or threads are the basis for producing packaging, tableware, textiles, 3D printing filaments, and other products. Polylactide has high transparency, strength, and heat resistance, making it an ideal substitute for traditional plastic. Polylactide granules are poured into special machines, extruders or thermopresses. There, they're heated to the required temperature until they become a viscous mass. The hot mass is passed through forms or dies. For packaging and bags, the extrusion method is used, that is, pulling hot polymer into long ribbons or film. Cups, containers, spoons, and so on are made by filling corresponding forms with polymer under pressure. To create more complex shapes, like coffee lids, heated film is pressed to the form with a press. As soon as the product is formed, it's quickly cooled, with water, air, or special cooling plates. This is needed so the material hardens and doesn't deform. Finished products are trimmed, polished if needed, checked for quality, and packed for delivery. Before packing, each product undergoes visual inspection or automatic checking for defects, cracks, deformations, irregularities. In large productions, this is done by robotic systems with cameras and sensors. Defective products are often remelted, since polylactide allows reuse without quality loss. After final cooling, polylactide products, still warm from machine touch, set out on their last journey, to the packing line. Here, everything works smoothly. Mechanical arms carefully stack cups in perfect stacks, 50 in each. Product groups are wrapped in biodegradable film or cardboard boxes. Packaging can also be made of polylactide. That is, the product and its wrapper are made from the same material, which simplifies recycling. Afterward, labels are applied with information: polylactide type, production date, batch, disposal instructions. Finished boxes with products are stacked on pallets, wrapped with stretch film, which is often also bio, and sent to warehouses or to customers. Storage temperature is room temperature, but without excessive humidity, so polylactide doesn't start decomposing prematurely. Green packaging is no longer just fashion, but a demand of the times. Videos about plastic harm get millions of views, and brands are looking for alternatives that don't harm the environment. Polylactide from cane is one of the most promising options. After all, cane grows quickly, and the production process doesn't require crazy resources. Every year, humanity produces over 4 billion tons of concrete, more than any other material on the planet. It's what our cities, bridges, and roads are built from. But every crack is like a tiny timer ticking toward destruction, started the moment water seeps inside. Now imagine concrete that actually lives, breathes, and heals itself. No people, no repairs. Deep in labs across the Netherlands, USA, and Japan, a game-changing material is being born. Inside it, bacteria or microcapsules that can seal cracks on their own, just like skin healing after a wound. How is this even possible? How did a lifeless material gain the ability to regenerate? Stick around until the end, and you'll find out how scientists brought concrete to life. Self-healing concrete. Sounds like something out of a sci-fi movie, but it's already here. Scientists invented it to solve one of construction's biggest headaches: cracks. Regular concrete starts drying out and cracking over time from temperature swings, moisture, or just plain stress. And a crack isn't just a scratch. Water gets inside, the rebar starts rusting, the structure weakens, and eventually, you're looking at expensive repairs or even a collapse. That's why researchers decided to create concrete that can patch itself up, no human help required. Sounds crazy, but it's actually pretty logical. There are two main technologies that make this possible: microbiological and mineral. The first one uses real living organisms. So-called bioconcrete was developed by Dutch researchers, and the principle is pretty straightforward. They add special bacteria to regular concrete mix, usually Bacillus pseudofermis or Bacillus conii. These bacteria can stay dormant for years, like seeds in dry soil. Along with the bacteria, they add nutrients, usually calcium lactate. And while the concrete stays intact, the bacteria just sleep. But when a crack forms and moisture gets in, they wake up. That's when the real microscopic work begins. The bacteria start consuming the nutrient substrate and, through their life processes, produce calcium carbonate, basically the same mineral that makes up seashells and limestone. That's what seals the crack from the inside, like the concrete is fixing itself. The results are impressive. Micro cracks up to 0.03 of an inch can disappear completely within a few weeks. And all without human intervention, purely thanks to nature that's been built into an artificial material. The second technology is less alive, but no less impressive. Instead of bacteria, it uses chemistry. Tiny capsules are added to the concrete, containing an active substance inside. For example, epoxy resin or sodium silicate. These grain-sized capsules are evenly distributed throughout the mix. When the concrete cracks, some of the capsules burst too. The substance inside comes out, fills the crack, and hardens on contact with air or moisture. The result is the material literally heals itself. It's similar to how certain car paints can heal scratches with heat, except this process is way more complex and large-scale. The advantage of this approach is that it works even in dry conditions, where bacteria might not activate. The downside is cost. Creating the capsules is more complex, so this concrete is pricier. But when you calculate the cost of repairing bridges or tunnels, it becomes clear. The payoff is huge. Interestingly, these technologies don't cancel each other out. Some companies are experimenting with combining biological and chemical methods to create concrete that could self-heal under any conditions: underwater, in the desert, or in freezing cold. Testing shows that structures made with this concrete last 2 to 3 times longer than regular ones. Bridges, roads, dams, parking garages, all of this can be made nearly eternal. For example, the Netherlands already built a lakeside lifeguard station using bioconcrete, and after several years, it hasn't needed any repairs. The idea is spreading fast around the world. In the US, these materials are being tested in bridges, in the UK, in sidewalk paving, and in Japan, even in concrete for coastal reinforcements that have to withstand salt water. Regular concrete, even the highest quality, has a shelf life, roughly 50 years. After that, cracks start appearing, water penetrates inside, rebar rusts, and the structure gradually weakens. Self-healing concrete changes these rules. Thanks to bacteria or microcapsules, it can heal microdamage before it becomes a problem. That's why the service life of structures can nearly double, from 100 to 120 years. That means one bridge or building can stand for 2 human generations without major repairs. Sure, this material isn't cheap yet. It costs several times more than regular concrete, on average 3 to 5 times more. But if you look at the long game, it's totally worth it. Maintaining, repairing, and restoring structures costs governments and companies millions of dollars every year. Self-healing concrete cuts those costs to a minimum. Basically, it's like buying a car that changes its own oil and fixes its own brakes. Expensive upfront, but then smooth sailing and economical. The Netherlands became the real home of self-healing concrete. Right here, at Delft University of Technology, the idea emerged to add living bacteria to the mix that could repair concrete from the inside. The man behind this idea is Dutch microbiologist and engineer Hendrik Jonkers. Nature inspired him. He noticed that certain bacteria can survive in limestone rock and create mineral deposits, filling micro cracks in stone. That's when Jonkers asked himself, if nature can heal stone, why not make concrete that does the same? In the early 2000s, he started experiments with different bacterial strains, looking for ones that could withstand concrete's alkaline environment and stay viable for years. After numerous trials, the best candidates turned out to be Bacillus pseudofirmis and Bacillus conii, spores that can sleep for decades and activate only when moisture appears. Jonkers added them to concrete along with a food source, calcium lactate. The results were mind-blowing. When the concrete cracked, the bacteria woke up and produced calcium carbonate, which sealed the cracks like natural glue. Jonkers called his invention bioconcrete, and soon the whole world was talking about it. Later, Delft University launched a project to test bioconcrete under real-world conditions. In 2015, the Netherlands built the first lakeside structure using this material. Years later, it remained in excellent condition without any repairs. Now Jonkers' lab is working with construction companies and governments from other countries, perfecting the formula to make it cheaper and more accessible. The USA and UK bet on the mineral technology for self-healing concrete, which doesn't require living organisms, but works through special microcapsules with healing substances inside. These countries are actively investing in research on materials that can automatically restore minor damage without human involvement. The principle is pretty simple, but looks impressive. Capsules or microcapsules filled with special gel, epoxy resin, or sodium silicate are added to the concrete mix. When the concrete surface stays intact, the capsules preserve their contents without reacting with the environment. But as soon as a crack appears, the capsule ruptures and the liquid flows into the damaged zone. On contact with moisture or oxygen, the substance hardens, gluing the crack edges together and returning the structure's original strength. These systems are currently being tested in US Army labs and British research centers, including Cambridge University. In the UK, they're even building experimental road and bridge sections with this material to track how it behaves under rain, vibrations, and temperature swings. American experts went even further. They're experimenting with capsules that can activate multiple times. Inside these capsules are microgels that not only fill cracks, but also expand on contact with water, creating a hermetic barrier against corrosion. This is especially crucial for bridges and skyscrapers in coastal cities, where concrete constantly faces moisture and salts. Test results show that cracks up to a few hundredths of an inch wide can seal themselves in less than a week. And if the damage is larger, the process takes longer, but still happens without human involvement. Such technologies can significantly extend the service life of roads, tunnels, and even military structures, which is especially valuable under extreme loads. They extract it in mountains where stone is born from flames and pressure capable of crushing anything alive. Its formation takes hundreds of millions of years, and today, people cut it with diamonds at a speed of 20 miles per hour. But what if I told you that this shiny material, used to decorate palaces and statues, was once the bottom of an ancient ocean, and that every slab of marble is a frozen story of life, death, and time? Watch until the end. and you will see how nature creates its own masterpiece, and people try to uncover its secret. Marble is not just a beautiful stone for decoration or sculpture. It is a material that has millions of years of geological transformation behind it. Its journey begins deep underground, where temperature and pressure change ordinary rocks beyond recognition. The basis of most marble is limestone, a sedimentary rock formed mainly from calcite. Limestone is formed at the bottom of ancient seas and oceans from the remains of marine organisms, corals, mollusks, foraminifera. Over millions of years, these fragments settle, compact, and cement together under pressure to form thick layers. When such layers fall into a zone of tectonic processes, where the Earth's crust moves, compresses, or subsides, they sink into deeper layers of the Earth. There, the temperature can exceed 1,200 degrees Fahrenheit, and the pressure reaches 1,000 atmospheres. Under these conditions, metamorphism begins, the process of transforming rocks without complete melting, but with a change in their structure. During metamorphism, the calcite crystals in the limestone begin to recrystallize. The old grains disappear, and instead, new ones grow, larger, tightly fused together. This process gradually transforms the loose sedimentary rock into a solid monolith with a characteristic shine and granular texture. It is this structure that gives marble its famous ability to be polished. The variety of colors and patterns in marble is the result of impurities that got into the limestone during its formation or metamorphism. If there is iron in the rock, the marble acquires reddish or yellow hues. Graphite or organic matter makes it gray or black. Impurities of serpentinite or chlorite add green tones. Quartz, dolomite, and pyrite create veins, the same patterns that make marble seem alive. Marble is not formed instantly. The process can take hundreds of millions of years. In places where tectonic plates collide, for example, in the Himalayas, the Alps, or the Apennine Peninsula, the rocks experience the most intense pressure. That is why such areas have become world centers for marble quarrying. For example, Carrara in Italy, where white marble of extraordinary purity was formed. During metamorphism, degassing also occurs, the release of carbon dioxide that remained in the pores of the limestone. Because of this, the structure of marble becomes almost non-porous. This density makes it durable, but also more brittle with sudden changes in temperature. In some cases, the process of marble formation can be partially reversible. If the temperature is too high, the calcite begins to melt, forming intermediate forms between metamorphic and igneous rocks. Such transitional marbles are found in areas of contact between limestone and magmatic intrusions, for example, near granite massifs. Another interesting feature is the zonation of formation. In nature, it is rare for an entire layer of marble to have the same structure. In different areas, the pressure and temperature are different, so some layers are coarse-grained, others are fine-grained, some have veins, others have a uniform color. This explains why even within a single quarry, marble of a completely different appearance can be extracted. When geologists study deposits, they are looking for precisely those places where the limestone has undergone complete metamorphism, but has not been destroyed by excess heat or deformation. Sometimes these layers lie at a depth of several hundred feet. Sometimes they come right to the surface, as in Tuscany or Greece. The quarrying and processing of marble is no less fascinating a process than its formation. The modern marble industry combines powerful machinery, precise laser technologies, and artisanal craftsmanship that has barely changed since the time of Michelangelo. The first stage is the identification of the deposit. Geologists conduct research on mountain ranges using georadar, laser scanning, and drilling samples. The goal is to find a layer of marble of the required thickness, color, and uniformity. Sometimes the required layer lies almost on the surface, as in Carrara in Italy, or on the island of Paros in Greece. In other cases, it has to be uncovered, removing tens of feet of rock from above. When the site is prepared, the separation of marble blocks begins. Once, this was done with explosives, but now much more precise and safer methods are used. The main tool is diamond wire saws. This is a steel cable on which hundreds of diamond segments are strung. The cable is stretched between two pulleys and rotates at a speed of over 20 miles per hour, gradually cutting the stone like a string cuts cheese. Thanks to a water cooling system, the cut is even and smooth, without cracks. Another method is drilling vertical and horizontal holes in the rock, through which a diamond wire is then threaded. This forms the rectangular contour of the block. When the cuts are connected, a huge piece of marble, usually weighing from 20 to 50 tons, is separated from the mountain massif. It is propped up with hydraulic jacks, steel wedges are inserted, and the block is gradually released, preventing a sudden fall. Next, the blocks are transported from the quarry to processing plants. On the slopes of mountains, powerful tracked loaders and platforms on heavy trailers are often used for this. In mountainous areas where there are no roads, marble is sometimes lowered by special cable systems, a kind of funicular that leads from the quarry to the valley. In the workshops, the blocks are cut into slabs or blanks. For this, gang saws are used, large frame machines with dozens of steel blades, between which an abrasive mixture with water is fed. In modern production, they have been replaced by diamond circular saws or laser cutting machines. The cutting accuracy reaches fractions of a millimeter. After cutting, the surface of the slabs is ground with abrasive stones of different grits, gradually moving from rough grinding to mirror polishing. If the marble is intended for architectural projects, it is further strengthened. A thin layer of resin or fiberglass is applied to the backside. This prevents chipping during transportation and installation. For sculptures, such reinforcement is not done. On the contrary, they look for a stone with a uniform texture without microcracks. Polishing is a separate art. It is performed on large machines where a series of round abrasive discs pass over the surface, gradually giving it a deep shine. To achieve a perfect effect, powders of tin or cerium oxide are used. It is they who reveal the structure of calcite, and the marble begins to play with reflected light. After polishing, the marble slabs are marked and sorted by color, pattern, and quality. Part of it is sent for export, another part to workshops for carving, facing, or manufacturing architectural details. Sculptors work with marble much more delicately. They use hand chisels, hammers, and now, pneumatic tools that allow them to carefully remove the stone layer by layer. Even with modern technologies, the art of marble processing remains semi-artisanal. It requires an eye, a touch, and an understanding of how the rock behaves. At the end, the marble products are coated with protective waxes or silicone impregnations, which enhance the shine and protect the surface from moisture. For interior work, softer compositions are used. For facades, water-repellent, UV-resistant ones. Quarries are usually located in mountainous areas that are difficult to reach. To cut blocks weighing from 20 to 50 tons, expensive equipment is needed. Diamond wires, cranes, hydraulic jacks. At the same time, about 30 or 40% of the quarried stone is suitable for commercial use. The rest is cracked or defective blocks that go to waste or are crushed into crumb. Due to the mass and fragility of the slabs, they are transported on special trailers or containers with cushioning. For imported marble, delivery can account for up to 30% of the final price. In every country, asphalt is just a road. But in Dubai, it's a challenge to nature. Here, air temperatures reach 122 degrees in the shade, while the road surface heats up to 160. Regular asphalt would melt within just a few days, but engineers found a way to make it survive. Polymers that hold their shape even at 176 degrees, geotextile membranes that breathe, and sensors that detect defects before human eyes can spot them. Why don't these roads melt like ice in the sun? And what strange technology did they test to make them actually dry after rain? Watch till the end. The finale will surprise you. Standard asphalt consists of stone aggregate and bitumen, a dark, thick substance that holds the mixture together, making it uniform and strong. However, bitumen has one weakness. It starts to soften at temperatures around 113 degrees Fahrenheit. For countries with moderate climates, this isn't a problem since road surfaces rarely reach such heating levels. But Dubai has completely different conditions. There, summer air can heat up to 122 degrees in the shade, while the road surface under direct sunlight can reach 160 degrees. Under such conditions, regular asphalt would literally behave like warm rubber. It would become soft, start deforming under vehicle weight, and in places simply slide off slopes. Plus, sharp temperature changes between scorching days and relatively cool nights would cause cracks to appear. In countries where occasional short heat waves occur, people might not immediately notice these processes. Sure, we sometimes get 104 degrees in summer, but such temperatures don't last long, and the surface deteriorates slowly, gradually. In Dubai, however, high temperature isn't just present, it's constant and stable for several months. This means asphalt is under continuous stress, and if you don't account for this factor, the road literally won't survive. That's exactly why engineers had to find a solution that would allow asphalt to maintain its shape even under extreme heating conditions. They replaced regular bitumen with modified bitumen, with polymer additives that change its physical properties. Such bitumen holds its shape at temperatures up to 176 degrees Fahrenheit. This means even when the road surface heats up to maximum levels, the material still remains stable, doesn't flow, and doesn't change structure. The difference might seem small at first glance. What's a few dozen extra degrees? But this exact difference makes Dubai's roads smooth, even, and durable, even when it's almost impossible to breathe from the heat around you. So what is this modified bitumen? The process is based on mixing bitumen with polymer additives. Polymers act like a reinforcing network at the molecular level. They stretch the bitumen structure, making it more elastic and heat-resistant. As a result, the asphalt doesn't soften. It maintains stability and shape even when heavy bus or truck wheels press on it for hours. The mixing process also isn't limited to just adding polymers. It's crucial to properly select the stone aggregate composition. Stones of different sizes create a framework-like structure, and bitumen here acts not as the main material, but rather as what connects the elements together. If the aggregate is selected incorrectly, bitumen will have to take on too much load, and even the modified mixture will lose stability. Therefore, asphalt composition is always a precise calculation of material ratios that don't just connect, but work as a unified system. But asphalt is just the surface. Hidden beneath it is a multi-layered sandwich that determines the road's durability. The first layer is sand, but regular sand won't work. It's mobile, can shift, and the road would lose its evenness within months. So sand is stabilized by mixing it with cement or special substances that make the mixture less mobile. Next comes a crushed stone layer that provides hardness and distributes load. Special geotextile fabrics can be laid between layers, preventing settling and material mixing. Geotextile works as a membrane that allows water to pass through, but doesn't let soil particles mix. This keeps the construction stable for many years. The way asphalt is actually laid also plays an important role. Work is usually done at night when temperatures are lower. This is necessary so bitumen cools evenly and gains the required hardness. If you lay asphalt during daytime heat, its surface will cool unevenly, creating stress in the structure that will eventually lead to microcracks. After laying, roads are regularly checked using special machines equipped with sensors and thermal imaging cameras. If sections are found where temperature is too high or irregularities appear, they're repaired immediately, not waiting until the problem becomes visible to drivers. Experiments with cooling coatings deserve special mention. In some districts, asphalt is painted or covered with a special compound that reflects sunlight and reduces surface heating by 10 to 15 degrees. This is important in pedestrian areas since road surface temperature affects how hot the air gets at foot level. This way, even a regular walk becomes less exhausting. In Dubai, roads aren't left unattended until large potholes appear. Control happens constantly and systematically. Special vehicles with measuring equipment travel highways and city streets, recording the smallest irregularities. Sensors read surface deviations, and computers compare them to standards. If there's suspicion of overheating or beginning deformation, the section is checked with thermal imaging cameras. High temperature indicates that bitumen is losing rigidity, and the surface might start settling. Thanks to such monitoring, repairs are done not when it's too late, but when the first changes begin. Repair work is conducted mainly at night when temperatures are lower and material cools evenly. This extends the road's service life and avoids repeated damage. The approach is based on the idea that infrastructure should work continuously, not wait for the moment when it becomes a problem for drivers. According to Dubai municipality data, after switching to polymer-modified mixtures, the number of deformation waves on roads decreased by approximately 40% during the first 2 years. Meanwhile, road surface service life increased on average from 7 to 10 years to 12 to 15 years before the first major repair. This significantly reduces overall infrastructure costs. Although initial polymer asphalt installation costs are higher by approximately 15 to 20%, long-term savings can reach 50% due to reduced repair needs. There's also data on experimental light reflective coatings being tested in residential areas and near pedestrian zones. On average, such coatings reduce road surface temperature by 10, or even all 14 degrees, depending on conditions. According to observations, in areas with cooling roads, air temperature at pedestrian foot level also drops by 2 to 3 degrees, reducing thermal load on people and making outdoor stays more comfortable. Statistics also show that, with early detection of surface microdefects, their elimination takes on average 3 to 6 hours, while if you wait for visible damage to appear, repairs can last from several days to several weeks and require closing road sections. Therefore, the city focuses on regular monitoring. In 1 month, control vehicles can cover over 80% of the city's road network. Dubai once tested asphalt that absorbs solar energy, then radiates stored heat at night to dry roads faster after rare rainfall. Turns out, the surface works like a giant thermos. During the day, it accumulates energy, and at night gradually releases it. The experiment showed such roads can dry 30% faster. And this is really needed, because after desert rain, water doesn't absorb into the ground, but can stand on asphalt for hours or even days. So the technology solves a problem that doesn't even exist in most countries. You know how this experiment ended? Every single second, over 100 tons of new trash gets created around the world. Think about it. While you're watching this video, an entire truckload of waste appears on our planet. Where does it all end up? For years, the answer was simple: China. That's where Europe, America, and Japan shipped millions of tons of used bottles, paper, and scrap metal. But one day, China said, "That's enough." And suddenly, the world faced a garbage meltdown. But here's the mystery. Why would a country that banned importing other people's trash start searching for it just a few years later? Stick around till the end. You'll discover the secret that flipped the global recycling industry upside down. For many, many years, the entire world, especially wealthy countries in Europe, America, and Japan, got comfortable with a very convenient setup. They'd collect their trash, old plastic, paper, scrap metal, and simply ship it off to China. Massive container ships sailed across the oceans, loaded with tons of used soda bottles, old newspapers, and broken toys. China was like the world's global trash can. But not just a can. It was also a massive recycling operation. Chinese factories would take this waste, sort it, process it, and turn it into new products that they'd sell right back around the world. It was incredibly profitable for China. They got cheap raw materials and created jobs. And for other countries, it was perfect. They got rid of their garbage problem for relatively little money. Everybody was happy, right? Well, almost. But then, around 2018, China said, "Enough." Imagine a huge meeting of Chinese officials where the decision rang out: "We're done accepting other people's trash." They called this policy, very characteristically, National Sword. It was like if your neighbor, whose garage you'd been dumping your junk in for years, suddenly said, "That's it, take it all back. My garage is full and I'm sick of this." And that's when real chaos erupted. Countries that had been carelessly shipping their waste to China for years suddenly found themselves with millions of tons of garbage with nowhere to go. Picture this. Warehouses across Europe and America started filling up with mountains of plastic and paper that were supposed to sail to China, but now had no destination. It was a genuine shock to their recycling industry. What were they supposed to do with all this trash? Dump it in the Pacific Ocean? Toss it in deserts like in post-apocalyptic movies? Of course not, but the panic was massive. Some countries started burning waste in incinerators, which isn't great for the environment since it pollutes the air. Others scrambled to find new trash cans in Southeast Asia, Vietnam, Malaysia, Indonesia. But these countries quickly started pushing back too, because they didn't want to become the world's dumping grounds either. But here's where it gets really interesting. While the world frantically searched for somewhere to shove their plastic mountains, China started feeling a strange hunger. A hunger for plastic, a hunger for waste paper, a hunger for scrap metal. Seems impossible, right? A country that generates the most trash in the world suddenly experiencing a shortage of it? It's like a millionaire who suddenly went broke and is now searching for loose change under the couch cushions. The thing is, Chinese industry had gotten hooked on this imported high. Recycling plants, of which there were, to put it mildly, plenty in the Middle Kingdom, had gotten used to working with cheap, abundant, though not always quality, imported waste. Imagine a huge factory that processes tons of plastic bottles from Germany or the US every day. Its conveyor belts ran non-stop. Its workers knew their job. Its owners counted their profits. And suddenly, bam! The tap of imported raw materials got turned off. National Sword didn't just cut off imports. It left this entire massive industry without its usual food supply. Factories stood idle, capacity sat unused, and business owners pulled their hair out. But why couldn't they just switch to their own Chinese garbage? After all, there are billions of tons of it, right? That's where the devil's in the details. The problem isn't the absence of trash altogether, but the absence of quality, sorted, clean raw materials. The problem is that Chinese citizens don't know how to sort trash. Imagine this. People lived for decades, just like we used to, following the principle of everything in one bin, then off to the dump somewhere. That's the easiest way, you gotta admit. No need to think about anything. No need to separate anything. Just toss it and forget it. And this system that formed over generations, this habit that took root deeper than the oldest tree, suddenly turned out to be wrong. The Chinese government, facing these trash mountains growing faster than bamboo after rain, decided, yeah, this has to stop. We're starting to sort. But something went wrong. Sure, in big cities like Shanghai, where millions of people live in tight quarters, they started implementing mandatory waste separation. Imagine, now you don't just throw out trash, you have to divide it into 4, sometimes 5 different categories. Wet waste, dry waste, recyclable waste, and hazardous waste. And all this has to be thrown out at strictly defined times, in strictly defined containers. But that's just the tip of the iceberg. First, even what gets sorted often doesn't meet the cleanliness standards required for recycling. Imagine a plastic bottle you tossed in the right container, but it was poorly washed and still had yogurt residue inside. Or a pizza box soaked with grease. Things like this, if there are too many of them, can ruin an entire batch of raw materials, making it unsuitable for recycling. Recycling plants that previously worked with more or less standardized imported plastic that had already gone through initial sorting abroad suddenly faced Chinese reality, a mixture that requires additional, expensive cleaning stages, or simply gets rejected. Second, logistics. Collecting billions of tons of trash is one thing, but collecting it in such a way that it reaches recycling plants as clean, sorted raw materials that can be economically viable to recycle, that's a completely different story. In many areas of China, especially in smaller cities and rural areas, the secondary raw material collection system is still very primitive. There, trash is still collected haphazardly, and sorting often happens right at the dump site, by hand, which hardly guarantees high quality. But there's another interesting angle here. China is a country that's constantly trying to upgrade itself, to become a leader in everything. And with trash recycling, it's the same story. After National Sword, they decided, okay, if we can't import, we'll build the world's best system ourselves. And they started building, modernizing, investing. New, modern, high-tech recycling plants appeared. They're equipped with the latest equipment, capable of processing massive volumes of secondary raw materials. But they need these raw materials. Clean, quality, preferably pre-sorted. And that's where the paradox emerges. There are plants, there's technology, there's the will to recycle, but there's not enough of the right trash. Picture a giant gleaming factory where robots work, but the conveyor belts move sluggishly because trucks haven't brought enough quality plastic. Or they brought it, but it's so contaminated that it has to be sent to the landfill instead of being recycled. It's like building a luxury restaurant with the best chefs, but having a shortage of fresh ingredients. This hunger for trash isn't just an economic problem, it's also a driver for further change. It's forcing China to accelerate reforms in waste management. The government is putting even more pressure on cities to improve their waste separation and sorting systems, educate the public, and implement fines for improper sorting. New logistics chains are being created for efficient collection and transportation of sorted secondary raw materials to recycling plants. Systems based on artificial intelligence and robotics are being developed for more accurate and efficient trash sorting. Imagine sorting robots analyzing every piece of plastic, determining its type and cleanliness. China aims not only to recycle, but also to use recycled materials in its own production, thereby closing the circular economy loop. This means that a system that previously relied on external sources of raw materials now has to completely reorient itself to internal, more finicky sources. And this trash hunger paradoxically pushes China to finally build a truly efficient and environmentally responsible waste management system. It's like a dragon that created a problem for itself just to heroically solve it later. And who knows, maybe in a few years, China will be not only the world's biggest trash producer, but also its biggest and most efficient recycler. That's the tangled but fascinating trash story from the Middle Kingdom. Every year, the world builds hundreds of miles of underground tunnels, but almost nobody thinks about what's holding them up above our heads. Picture this: thousands of concrete segments, each weighing several tons, assembled with precision down to the millimeter, forming tunnels where trains blast through at dozens of miles per hour. Now here's the big question. What happens if even one of them is made wrong? Today, we're diving into the place where the backbone of the subway is born, where one tiny mistake can cost millions or more. But there's a detail they usually don't show. Stick around till the end, and you'll find out what's actually hidden inside these concrete rings. Let's start with what a tunnel lining segment is, and why we need it. When a tunnel boring machine grinds its way through soil, you've got to shore up the tunnel walls right behind it, because soil isn't rock and won't hold itself up. The shield pushes forward, and behind it, installers assemble a ring from several segments, usually 5 to 8 pieces plus one keystone. The assembled ring is what you see when you're riding the subway and looking out the window. Uniform concrete sections with bolted connections along the seams. Looks mundane. Actually, an engineering solution refined over more than 150 years. The plant I visited manufactures tunnel segments for the city subway. Tunnel diameter, 21 feet. Each ring consists of 6 segments and 1 keystone. Width of one ring along the tunnel axis, 5 feet. Concrete wall thickness, 18 inches. One segment weighs close to 4,500 pounds. Monthly, the plant ships out about 600 rings, meaning over 4,000 segments. The math comes out monumental. It all starts with rebar cages. This is the exact moment when steel rods transform into a three-dimensional structure that'll end up inside concrete and keep it from cracking under load. The rods get cut and bent on automated lines. The machine receives a program, selects the right wire diameter, bends it at the specified angle, and cuts it to size. The thinnest rods here are about 1/4 inch in diameter, the thickest around 1 inch. Then the cages are assembled by hand or welding. It's tedious and monotonous, and workers here are clearly grateful when automation handles the whole process. The finished cage gets placed into a steel mold. The mold is probably the most expensive thing in these entire factories after the presses themselves. It's manufactured for a specific project and specific tunnel diameter. One mold costs anywhere from $200,000 to $400,000, depending on the complexity of the geometry, and it's rated for several thousand cycles. Before each pour, the mold gets cleaned of leftovers from the previous cycle and coated with special release compound. Without it, concrete bonds to the steel permanently, and you can't pull the segment out without damage. The lubing process is its own science. Too much creates pores on the concrete surface, too little ruins the mold and wrecks the piece. Seems minor, but at the plant, they train people separately just for this. Next, concrete. They don't pour regular batch plant mix here. Segments get made from special grade concrete with precisely dialed in water cement ratios, aggregate size, and additives. Compressive strength, not less than 6,000 pounds per square inch. For comparison, concrete in typical residential construction runs around 3,000. This stuff is twice as dense and heavy. Additives in the mix ensure waterproofing, because subway tunnels run below the water table, and the concrete has to hold water back completely, not soak it up like a sponge. The mix is prepared in an automated plant right at the factory and delivered to the form by transport conveyor or buckets. They don't pour the entire form at once. They do it in layers with vibration in between. Vibrators plunge into the concrete, and when switched on, the vibrator squeezes out air bubbles from the mix. If you leave air in, the concrete will have voids, and porous concrete lets water through and is less strong. One segment takes anywhere from 45 minutes to an hour, accounting for all the layers and vibration. Rushing here is harmful. This is one of those cases where slower actually means better. The filled form heads into a heat treatment chamber. Steam curing, that's what it's called. The temperature inside, around 100 degrees Fahrenheit, humidity high. The goal, speed up cement hydration and let the concrete gain sufficient initial strength in 8 to 10 hours, instead of the standard 28 days. After curing, the concrete has about 70% of its design strength, enough to remove the formwork without risk of damaging the product. Demolding, the moment I hold my breath a little every time. The crane operator lifts the top part of the mold, then the side panels swing away, and the segment stands on its own. A concrete arc that was just a sloppy mix 8 hours ago. Looks solid. No wonder. 14,000 pounds of solid concrete with rebar in the center. Next, the segment gets moved by crane to a curing rack, where it'll sit for another 7 to 14 days, until it reaches full design strength. Quality control runs parallel to all this. And it's serious here, because tunnel segments aren't paving stones. Each piece gets marked and assigned a unique identification number. During the pour, they pull test cubes, small concrete cubes measuring 4 by 4 inches, that later get crushed in a press to measure the actual strength of the batch. At the same time, ultrasonic testing of finished segments. The ultrasonic device presses against the surface and measures the speed of the wave passing through the concrete. Dense, uniform concrete gives one reading, concrete with hidden cracks or voids, another. The difference shows up immediately, and that segment gets rejected. Another type of control is geometric. Each segment gets placed on a measurement stand and all key dimensions get checked. Arc length, thickness, bolt hole positions, surface flatness. Bolt hole tolerance can't exceed 1/32 of an inch. Segments that fall outside tolerances, and it happens more often than manufacturers are willing to admit publicly, either get sent back for rework or scrapped. On large projects, the rejection rate can run anywhere from 1 to 3% of total output. Doesn't sound like much at first, but when a single segment runs $4,000 to $6,000, it adds up fast. A separate curiosity, the waterproofing profile. Around the perimeter of each segment, there's a special groove. A rubber gasket fits in there. When the segments get compressed by bolts into a ring, the rubber deforms and hermetically seals the joint. This rubber profile looks like an ordinary black strip, gets manufactured from a highly specific compound based on chloroprene rubber, withstands pressure up to 120 pounds per square inch, and lasts as long as the tunnel itself, meaning it's designed for a minimum of 100 years. Rubber that'll outlive you and me both. Bit philosophical. Shipping from the factory isn't exactly simple either. The segments are heavy, fragile around the edges, and demand careful handling. They're loaded onto specialized frames, secured with tie-downs, and a flatbed truck hauls them to the construction site. There are limits on stacking height, no more than 3 tiers, because the bottom segments can't take excessive weight from above. At the construction site, they dig a vertical shaft. The segments get lowered underground and assembled into rings right behind the shield as it pushes forward. The shield advances 5 feet, the width of one ring, and the crew installs the next one. This rhythm never stops, day or night. I step out of the plant and stop beside a stack of finished segments. Gray, slightly rough, smelling of cement. Totally unremarkable. In a few weeks, they'll be 50 feet below city streets, just sitting there. As long as the city stands. No days off, no maintenance, no attention whatsoever from the people above them. That's the fate of a concrete arc weighing 4,000 pounds. I'd complain, but the concrete doesn't seem to mind. See you on the next tour. So, I know North Carolina doesn't sound particularly exotic, but what's being made here flies at 66,000 feet above the Pacific Ocean and keeps 400 passengers in the air at the same time. This is the factory that produces blades for the GE9X turbine engine series, the largest commercial jet engines in the world today. One of these engines weighs about 9 tons, generates thrust up to 105,000 pounds. Sorry, that's roughly 460 kilonewtons, and costs around $50 million. But we're not here because of the engine. We're here because of one specific part that's about the size of your palm and costs more than a nice car. A turbine blade. In the hot section of the engine, in what's called the high-pressure turbine, there are between 160 and 180 of them per wheel, depending on the stage. Each one weighs roughly 10.5 to 14 ounces. But the conditions it operates in, this isn't engineering anymore. It's straight-up torture for common sense. The temperature of the gases flowing around the blade during engine operation, 2,700 to 2,900 degrees Fahrenheit. That's higher than the melting point of steel, higher than the melting point of the very material the blade is made from. How it doesn't just melt, I'll tell you in a minute, because it's one of the coolest things I saw at this facility. The blade material is a nickel-based superalloy. The exact recipe is classified, and they didn't tell me the full breakdown, which is fair. But the general principle is known. Each element is responsible for something specific. Take rhenium, for instance. It provides heat resistance and slows down creep. That's when metal under prolonged stress and temperature deforms completely. The raw material cost for a single blade runs from 200 to 300 euros just for the metal, before anyone's even touched it. Now, how it all begins. The blade manufacturing process is investment casting, also known in the industry as lost wax casting. First step, the wax model. An exact replica of the future blade including all internal channels, is created from wax under pressure in a metal mold. The precision of this mold, plus or minus 20 micrometers. That's about a quarter of the thickness of a human hair. If the mold deviates any more than that, it goes back for refinement. But the wax model is just the outer form. Inside the blade, there are also cooling channels, thin, winding tunnels through which cold air from the compressor gets pumped during engine operation. That's why the blade doesn't melt, even though the surrounding gas is hotter than its own melting point. Inside, air at temperatures of 500 to 600 degrees Celsius flows through and keeps the metal in the working zone. These channels are formed separately, using ceramic cores that get inserted into the wax model before casting. The core looks like a thin, sturdy comb, and it occupies exactly the space where the channel will eventually be. The wall thickness between the blade's outer contour and the internal channel ranges from 1 to 2 millimeters. Any thinner, and the blade becomes brittle. Any thicker, and the cooling can't keep up. Next, the wax model gets dipped into a liquid ceramic slurry and coated with fine ceramic sand. Dip, pull out, dry, and repeat the cycle 8 to 12 times. Each layer dries for 4 to 8 hours. After the final layer, you get a ceramic blob about 10 millimeters thick, hard, rough to the touch, kind of like papier-mâché if papier-mâché were made from space shuttle material. Then this whole thing, with the wax still inside, goes into an autoclave, where at temperatures around 300 degrees Fahrenheit and elevated pressure, the wax melts out through a small opening. Hence the name, lost wax casting. What's left inside is a perfect negative of the blade shape. The ceramic holds its form, the cores stay in place. Now comes the metal pour. This is the part I came for. The molten metal gets heated to around 2500 to 2700 degrees Fahrenheit and poured into the ceramic mold. But they don't just pour it and wait for it to solidify. The mold gets slowly withdrawn from the heating chamber at a rate of about 1/10 to 1/5 of an inch per minute. That withdrawal speed controls how the metal crystallizes. If everything's done right, the entire blade, from root to tip, becomes a single crystal. Not a single grain boundary throughout the entire volume of metal. That's single crystal casting. Grain boundaries, the weakest spot in any metal. That's where cracks start under prolonged stress and heat. If there's only one grain, there's no boundary, no failure points. Heat resistance jumps roughly 30% compared to ordinary polycrystalline casting. After cooling, they break the ceramic shell, just mechanically, with hammers and vibration. Out comes a gray blade with ceramic cores inside. The cores come out in an alkaline solution at roughly 210 degrees. The chemistry dissolves ceramic, but leaves the metal untouched. This takes 4 to 8 hours. After washing, those same cooling channels remain in the center, clean, precise, completely open. Then they check the blade. X-rays reveal pores and cracks inside the metal. Fluorescent liquid catches surface defects. A special probe passes through each cooling channel, verifying it's not blocked by ceramic residue. If even one cooling channel is partially blocked, the blade goes straight to scrap. Not to rework, straight to scrap. Because you can't fix that. The rejection rate at this stage runs 2 to 5% per batch. Doesn't sound like much, but given what each part costs, we're talking real money. After inspection, heat treatment. The blade goes through multiple temperature cycles. First, around 1900 degrees for several hours, then a gradual cool down. This process evens out the internal stresses that formed during casting and locks in the alloy's microstructure. The exact heat treatment protocol? Also classified. When I asked, the manager who was walking me through just smiled and changed the subject. Final stage, protective coatings. First comes a metallic bond coat, nickel and aluminum based, applied using a plasma spray process. That's the foundation. On top of that goes the thermal barrier coating, zirconia stabilized with yttrium. It's ceramic. And it's that ceramic layer that absorbs the first several hundred degrees from the screaming hot gas stream. This layer is between 100 and 2 micrometers thick. The application looks like spray painting in a chamber. The blade rotates, the plasma gun moves along it, following a preset path. But the temperature of the plasma stream during application is around 18,000 degrees Fahrenheit. For comparison, the surface of the Sun is about 10,000 degrees. So the tool is nearly twice as hot as a star, but the blade itself doesn't heat up more than 4 degrees, because the entire process is incredibly fast and incredibly precisely controlled. The finished blade goes for final weighing, measurement, and registration. Each one gets an individual serial number and a passport where all parameters are recorded, from the chemical composition of the melt to the results of every control measurement. This document is kept for as long as the engine lives, and that's 20 to 30 years and tens of thousands of flight hours. On my way out, I asked how many blades they made per month. They told me it was in the range of several thousand units across all sizes. They wouldn't give me an exact number. But when you consider that one engine needs several hundred hot section blades alone, and orders for the 9X remain backed up for years ahead, you can imagine the scale. You're the best. Subscribe so you don't miss the next facility. It's going to be even more interesting. Write in the comments where you're from, and maybe next time I'll visit your city. Today, we're not at some sleek, modern factory. We're heading back in time, to an era when the entire world was engulfed in flames, and one nation that had peacefully built cars and refrigerators did something absolutely mind-blowing. This is the story of the arsenal of democracy, how American industry churned out so much weaponry in just a few years. It could have armed several planets. And we're looking at its crown jewel, the legendary flying fortress, the B-17 bomber. I spent weeks digging through archival blueprints, photographs, and records to tell you how a country that was making sedans for housewives yesterday started rolling out one bomber every single hour. So it's December 1941. Pearl Harbor's in flames, and America enters World War II. And the first question facing the government: where do we get planes? The B-17 bomber, developed by Boeing. It's an engineering marvel, but they're building barely any, almost one at a time. And the country doesn't need dozens. It needs tens of thousands of these machines. So President Roosevelt throws down the gauntlet to American industry, and that industry answers. And how it answers. Enter automotive giants like Ford and aircraft companies Douglas and Lockheed. They're told, guys, forget about cars. From now on, you build bombers. And that's when the real madness begins. Picture this. Ford, a company that had never built planes before, constructs from scratch in the middle of a Michigan cornfield, the world's largest factory at the time. Willow Run. This isn't just a factory. It's an entire city under one roof, a mile long. Over 40,000 people work here, many of them women coming into manufacturing for the first time. And they face a task that seems impossible. Put the production of a giant, complex bomber on an automotive assembly line. Nobody had ever done this before. You get why it was women, right? When America entered the war, millions of men, factory workers, farmers, mechanics, put on military uniforms and shipped out to the front. And suddenly, the factories that needed to produce tanks, ships, and planes sat empty. The country faced a massive labor shortage. So the government and industry turned to people they'd barely considered for heavy manufacturing before: women. A powerful propaganda campaign rolled out. Famous posters showing a strong woman in a work bandana, flexing her bicep with the words, "We can do it," appeared across the country. And women answered the call. Millions of housewives, waitresses, secretaries, and recent high school graduates went to work in the factories. For them, this wasn't just a paycheck. It was patriotic duty, a way to do their part for victory, while their husbands, brothers, and sons fought thousands of miles from home. They proved they could do men's work just as well, sometimes better, becoming the unstoppable force that allowed American industry to work miracles. And here's where the American government and industry made some incredibly powerful moves. First, the government essentially forced Alcoa to share its technology and funded the construction of dozens of new, massive aluminum plants across the country. Entire cities were built, for example, in the industrial states of Washington and Tennessee. Why there? Because aluminum production is an insanely energy-intensive process. It relies on electrolysis from alumina, and that requires cheap electricity. And in these exact regions, the government had just finished building giant hydroelectric dams on the Columbia and Tennessee rivers. It was a perfect match. Huge amounts of clean, cheap energy waiting for someone to use it. Second, raw materials. The main raw material for aluminum is bauxite. Most of it had been imported from South America before the war. When the war started, German submarines began hunting merchant ships, and that route became dangerous. So America dramatically ramped up mining of its own bauxite, mainly in Arkansas, and secured the sea routes from the Caribbean as much as possible. But the most amazing part of this story is the grassroots movement. The government launched a massive patriotic campaign with the rallying cry, "Turn in aluminum for victory." School children, housewives, Boy Scouts, the entire nation started collecting aluminum scrap. People turned in old pots, pans, milk cans, parts from household appliances. It didn't have decisive economic significance, but it had a colossal psychological effect. Every American felt that their old pot could become part of a flying fortress wing that would fly off to strike the enemy. As a result of these titanic efforts, in just a few years, from 1940 to 1943, aluminum production in the US increased sixfold. The country didn't just cover its own needs, it started supplying this strategic metal to its allies. And that's how, through the combination of government will, industrial might, and the patriotism of ordinary people, America transformed a scarce pot metal into an endless stream of winged metal that became the lifeblood of its bomber armada. After stamping, each part needed 2 holes drilled on each side for rivets. And that's when the women stepped onto the stage. The legendary Rosie the Riveters. Thousands of young women who just yesterday were housewives or waitresses now stood at workstations, drilling these holes with incredible speed and precision. And then the real concert began. Thousands of pneumatic riveting hammers pounding aluminum simultaneously, creating a deafening non-stop roar. This was the sound of the arsenal of democracy being forged. Women worked in pairs. One held a massive bucking bar from the inside, while the other hammered the rivet from outside. Each rivet had to be perfect, because the aircraft's strength depended on it. And this is where Ford unveiled its main automotive trick, modular assembly. They didn't try to build the entire airplane in one place. Instead, they broke it down into large sections, or modules. In one shop, thousands of people assembled just the nose section of the fuselage. In another, just the center section with the bomb bay. In a third, gigantic wings, each over 50 feet long. Each section was assembled on its own mini assembly line, where it was packed with everything necessary. Miles of wiring were run, hydraulic lines installed, equipment mounts fitted. This allowed dozens of teams to work in parallel, without getting in each other's way. And then, these ready-made sections, packed with internal modules, looking like giant chunks of an aluminum construction set, got wheeled over to the main assembly line. This was the climax, a line a mile long. At the start, there's just the center wing section. Then 2 fuselage halves get joined to it. The whole structure moves freely forward. At the next station, they attach the nose and tail sections. Further down, they mount the massive wings. And so, step by step, right before your eyes, from separate pieces, a gigantic, nearly 100-foot aircraft takes shape. At the final stations, they install 4 powerful Wright cyclone engines, each churning out 1,200 horsepower, mount the landing gear, glaze the cockpit, and of course, fit its main argument: 13 heavy-caliber Browning M2 machine guns, which gave it the name Flying Fortress. At peak production, in 1944, the Willow Run plant rolled out one B-17 bomber every 63 minutes. Just think about that. Every hour, 24 hours a day, a brand new, battle-ready heavy bomber rolled through those factory gates. It was a non-stop river of steel, aluminum, and firepower. In total, during the war years, 3 companies, Boeing, Douglas, and Ford, built over 12,700 flying fortresses. This wasn't just a victory of technology, this was a victory of logistics, organization, and most importantly, people. 1.5 million ordinary Americans who put aside their peacetime lives and became soldiers on the industrial front. They proved that a free nation, when united by a common paycheck, is capable of genuine miracles. That was the arsenal of democracy in action. Thanks for watching. Hit that like button, subscribe, and see you next time. Every year, the world mines over 900,000 tons of rare earth metals. Without them, not a single smartphone, electric car, or wind turbine would work. But there's one place where most of them are born: Baiyun Obo, a massive quarry in the heart of China that supplies 70% of all the rare metals on the planet. Here, the earth glitters with metallic dust, and every dump truck hauls raw material for the future. But behind this shine hides a dark truth: lakes of toxic waste, and the price nature pays for technological progress. Stick around till the end, and you'll discover how dust and poison create the foundation of modern civilization. The story of Baiyun Obo started back in the 1920s, when geologists discovered a strange ore in this area, a mix of iron and minerals unknown at the time. In the 1950s, Chinese scientists realized that hidden here was a treasure trove of rare metals: neodymium, praseodymium, cerium, yttrium, and lanthanum. Since then, Baiyun Obo has become the heart of China's strategy that would eventually turn the country into the undisputed leader of the global rare earth market. Every year, about 270,000 tons of rare earth concentrate are mined here, more than all other countries combined. It all starts simply. Massive dump trucks the height of a 2-story building pull up to the edge of the quarry, where giant excavators with buckets like a dinosaur's mouth rip out chunks of monzonite ore. Each bucket can hold over 100 tons. The dust rises in columns, and it feels like the very air here is saturated with metal. But extracting the ore is just the beginning. The real value is hidden in microscopic inclusions of rare earth minerals. Their share in the rock is only a few percent, so after extraction, the ore is crushed and sent to processing plants, where a complex chemical story begins. First, the ore is ground to dust, then subjected to flotation, a process where particles suspended in water are separated using reagents. Rare earth particles stick to air bubbles, rise to the top, while the rest settles to the bottom. This is just the first step, because the concentrate still contains plenty of impurities: iron, calcium, fluorine. Next comes chemical extraction, which transforms the concentrate into high-purity oxides. This is an extremely complex process. In specialized reactors, the ore is treated with acids, usually sulfuric or hydrochloric, sometimes with the addition of fluoride compounds. After this, the resulting solution is separated into fractions using organic solvents. Each element, neodymium, praseodymium, cerium, has its own chemical quirks, so the process requires dozens of sequential cycles of extraction, precipitation, filtration, and drying. It's these oxides that then go into the production of permanent magnets, the main consumer of rare earth metals. For example, one iPhone might contain less than 1/10,000th of an ounce of neodymium in the speakers and vibration motor. In a modern wind turbine, nearly 1,400 pounds of this element. And here's the wow fact: Just 1 gram of neodymium can provide a magnet for a turbine that generates electricity for roughly 1,000 homes. It sounds like an energy miracle, but it has a flip side. The problem is that chemical processing of rare earth ores is extremely toxic. Every gram of pure metal means tons of waste. In the Baotou area, near Bayunobo, real waste lakes have formed. Black, acidic bodies of water where radioactive elements, fluorides, and heavy metals accumulate. They're visible even from satellite. Even with modern cleaning technologies, chemical processes leave their mark on the environment. Local residents tell stories that, over the past decades, dust from the quarry and processing plants has changed the soil color, and grass around the area has been growing worse. However, the Chinese government is taking measures. Implementing closed-loop water systems, controlling acidic runoff, and converting some facilities to new, green technologies, where instead of traditional acids, they use ionic solutions and membrane separation. All this is being done not just for environmental reasons, but also because China aims to maintain its dominance in the global rare earth metals market. Today, it accounts for 70% of global production and over 90% of finished oxide and magnet production. Other countries, the US, Australia, Vietnam, Malaysia, are trying to develop their own deposits, but they haven't come close to Chinese scales yet. Bayunobo has become more than just a quarry. It's a symbol of the technological era, where Earth transforms into smartphones and ore becomes electric wind. Right here, among mountains of metallic dust, the elements that power digital civilization are born. There's a certain irony in this. In the quest to create a green future, humanity has become dependent on one of the dirtiest industries. Magnets for electric cars and turbines, batteries, solar panels. All of this requires metals extracted from places like Bayunobo, and the greater the demand for clean energy grows, the deeper this giant wound in the earth becomes. Despite this, for China, Bayunobo is a source of national pride. Thousands of people work here, and the territory itself is equipped with modern infrastructure, conveyor systems, automated drilling rigs, chemical plants that operate almost without human involvement. On the surface, sensors are installed that track air composition, and in reservoirs, pollution levels are monitored in real time. Every dump truck descending into the quarry is part of a giant machine that supplies the world with energy, data, and sound. And when we hold a lightweight smartphone in our hands, it's worth remembering that a piece of this device, maybe even that very magnet in the speaker, was once dust in the Mongolian desert. Neodymium is one of the most famous, and at the same time, most mysterious rare earth metals. It's a silvery white, shiny, fairly soft metal that easily oxidizes in air, so it's usually stored under a layer of oil, or in an inert atmosphere. Sounds unremarkable, but this element has become the quiet engine of the modern technological revolution. Without neodymium, wind turbines, electric cars, headphones, laptops, and even rockets wouldn't work. In pure form, neodymium doesn't have the magnetic properties it's valued for. They appear when it's combined with iron and boron, forming an alloy. This is the material used to make the most powerful permanent magnets on Earth. One neodymium magnet can hold weight hundreds of times its own. In industry, it's called a supermagnet, and for good reason. It's what makes compact electric motors, miniature speakers, and highly efficient generators possible. One study indicates that between 2001 and 2021, Bayunobo supplied about 60% of neodymium from China's total neodymium extraction. On one hand, Bayunobo is a remote, harsh, and dusty place. On the other, it evokes an almost magnetic curiosity in those who want to see what modern civilization looks like in its raw material form. Bayunobo today is not just a mine, but an entire complex with its own small town, a rare earth elements museum, and even a special viewing platform from which you can see the giant pit going hundreds of feet deep. The flow of tourists here is small by Chinese standards, but steady. These are mainly engineers, geology students, bloggers, eco-tourists, and those fascinated by industrial landscapes. In 2019, local authorities even declared Bayun Obo part of the Industrial Heritage of Inner Mongolia route to show how mining and processing have transformed the region. In tourist brochures, this place is called the heart of the rare earth planet. The road to the quarry leads through endless plains and low hills, where the wind almost never stops. The air carries the smell of metal, and from a distance, the quarry looks like a giant amphitheater, where earth plays the starring role. Tourists aren't allowed close to the mining zone. It's too dangerous, but there are several safe spots from which you can take photos. The most striking moment is when quarry dump trucks slowly move at the bottom of the pit. They look like toys. The scale is so massive. Imagine construction that's not just strong, but super lightweight, durable, and eco-friendly all at once. That's exactly the revolution that fiberglass rebar represents. A modern material that's gradually replacing traditional steel reinforcement in countries around the world. China is especially aggressive in producing it, a giant controlling a massive chunk of the global market. But what is this secret material that's changing the game? And why does geopolitics play just as big a role here as technology? Let's dig in. Fiberglass rebar consists of reinforcing rods made from a composite material based on fiberglass soaked in special resins. Unlike traditional steel rebar, it's 4 to 5 times lighter, doesn't rust, resists corrosion, and holds up under harsh conditions. Think acid rain, salt spray, and high humidity. To put it in perspective, standard steel rebar weighs close to 1 pound per foot of length, while fiberglass rebar weighs about a quarter pound for the same size. This means it's easier to work with, requires less spending on transportation and installation, which makes construction faster and cheaper. China plays a leading role in global fiberglass rebar production. Factories, located mainly in the eastern and central regions of the country, are equipped with modern pressing, forming, and fiberglass polymerization lines. Chinese companies produce over 500 million pounds of these materials annually, with exports accounting for roughly 60% of total global volume. China's huge advantage lies not only in scale of production, but in price. Thanks to low electricity and resource costs, Chinese products are often cheaper than competitors from the USA and Europe. But this is already triggering intense geopolitical discussions. If you look at the bigger picture, fiberglass rebar has become a real hot potato in global trade. Western countries increasingly face a dilemma: support domestic production with significantly higher costs but less export influence from China, or actively import cheap Chinese rebar, becoming dependent on Chinese materials. This secret aspect is this: China uses fiberglass rebar not only in its own massive infrastructure projects. Through strategic investments in countries across Asia, Africa, and Latin America, Beijing actively promotes this material through its global construction corporations working within the Belt and Road Initiative. This allows China to not only increase its presence in the global construction market, but also strengthen economic influence in regions through control over construction resources. The trend of using fiberglass rebar isn't just about savings or new materials. It's about ecology and safety. Fiberglass rebar is rapidly gaining popularity in the USA, where the number of bridges, roads, and buildings constructed using lightweight composites is growing. Unlike metal, this material doesn't corrode, so infrastructure becomes more reliable and durable. According to reports from the American Association of Building Materials, on average, the cost of construction using fiberglass rebar drops by 20%, and the service life of structures doubles. For young engineers, architects, and entrepreneurs, this means more opportunities for innovation, reduced environmental impact, and industry growth. If you're building a bridge or a high-rise, instead of heavy steel rebar, you use thin fiberglass rods. They can be longer, lighter, and simpler to install. Plus, you don't have to worry that after years, they'll start rusting and causing concrete deterioration. China is already actively using its fiberglass rebar on huge construction sites. In the capital districts of Beijing, Shanghai, and Guangzhou, they're installing new highways and bridge crossings using these materials. Around the world, Chinese companies supply this rebar for projects in the USA, Europe, and Middle Eastern countries, strengthening their technological and economic presence. Everything starts with glass, the raw material for making fiberglass. Glass is made from a mixture of sand, limestone, and soda. These ingredients are sent to large furnace ovens, heated to temperatures of 2,700 degrees Fahrenheit. Here, the mixture melts, forming liquid glass. Then the molten glass passes through special openings called spinnerets, forming thousands of thin threads. These fibers are cooled and collected into bundles. This creates primary fiberglass, thin, flexible, and strong threads. To give the fibers necessary properties, they're treated with a special chemical solution, an organic binder or silane. This coating ensures strong adhesion between the fiberglass and the polymer matrix that will follow. The treated threads are collected into bundles that can contain thousands of individual fibers. These fibers are oriented parallel to each other for maximum strength. Next comes the main stage, forming the composite matrix. The raw material for this is polymer resins, usually epoxy, polyester, or vinyl, which have high strength characteristics and provide a resistance to moisture and chemical effects. The fiberglass bundles are dipped or soaked in the polymer resin solution. The fibers are evenly coated with polymer, and excess is removed so there are no lumps and irregularities. The prepared wet bundles are fed into a special forming line, an extruder. Here the molten composition is pushed through forming openings, giving it the shape of a rod or bar of the required diameter. Then comes an important operation, drawing and polymerization. The finished reinforcing rods are immediately sent for cooling and hardening in special thermal chambers. Here, the polymer matrix solidifies, firmly binding the fibers into a single structure. Size and shape control is very important, so production lines are equipped with automatic calibration systems to ensure the specified diameter and round shape of the rebar. Standard fiberglass rebar diameter can range from 1/4 inch to 1.5 inches, depending on the application. To ensure better adhesion to concrete, the rebar isn't left completely smooth. During production, an action occurs through forming rollers that creates ribs, notches, or texture on the surface. This makes fiberglass rebar more effective for reinforcing concrete structures. It holds firmly in the concrete mass and doesn't slip under loads. At the end of the production line, workers or automation cut the reinforcing rods to standard lengths, usually 20 feet or 40 feet. The rods are packed in bundles that are convenient to transport and store. Each batch of products undergoes testing for strength, flexibility, and corrosion resistance. Manufacturers often provide warranties for rebar service life of over 50 years, which is several times longer than the service life of ordinary metal reinforcement. Fiberglass rebar is gaining increasing importance in modern construction thanks to its lightness, strength, and corrosion resistance. Next, you'll see some of the most interesting projects where this innovative material is actively used. Delhi Metro Phase in India, a large-scale metro project where this rebar is actively used to reinforce tunnels and structures. This helps extend the service life of structures and reduce the weight of building materials. Jizan Flood Mitigation Channel, Saudi Arabia, the world's largest project using fiberglass rebar, involving reinforcement of long channels for flood control. Over 11 million meters of fiberglass rebar were used here, designed to ensure high resistance to harsh environments. Muskrat Falls Hydroelectric Project, Canada. Rebar manufacturers supply material for reinforcement that guarantees a long service life for the hydroelectric station, especially in conditions of contact with water and high humidity. Sunshine Skyway Rest Area. Seawall, USA, Florida. Marine structures where fiberglass rebar is the ideal material due to corrosion resistance in salt water. Here, it reduces the need for repairs and extends the service life of the walls. Alligator River Bridge, USA, North Carolina. A bridge reinforced with composite rebar to increase durability and minimize the weight of metal structures. Canadian tunnels. Toronto TTC North Subway Extension, a project where fiberglass rebar helps increase structural flexibility and reduce damage risks during seismic movements. In every second of our lives, there are metals we don't even suspect. Without them, there would be no smartphones, electric cars, or even jet aircraft. And now imagine a place where, in the middle of the desert, under the scorching California sun, the United States creates a strategic resource of the future, without a single pound of Chinese raw materials. Here, at Mountain Pass, they mine 43,000 tons of rare earth metals annually. Rocks that look ordinary are transformed into materials for lasers, engines, and defense systems. But there's something almost no one knows about. And if you watch till the end, you'll understand why this dust from the desert can change the world. Today here, in the dust and heat, MP Materials Company mines 43,000 tons of rare earth concentrate per year, all without a single pound of Chinese raw materials. For a country that for decades depended on imports from China, this is a strategic breakthrough. The main star of this place is bastnasite, a mineral that looks like an ordinary stone but contains treasures inside: lanthanum, cerium, neodymium, and praseodymium. These very elements give life to modern magnets, lasers, electric cars, and jet aircraft. Everything begins in the depths of the quarry. Huge excavators and 300-ton trucks carry rock to the crusher. Next comes the flotation process, similar to a magic sieve. Crushed ore is mixed with water and special reagents. All this turns into foam, and bastnasite particles float to the surface, while waste settles to the bottom. After flotation, bastnasite goes for chemical expertise. In MP Materials laboratories, it's transformed into concentrate, and then into individual elements. This is a complex sequence of extractions and washes, where each metal chooses its own path. Once, this stage was performed in China. Now the United States is gradually building a full production cycle, from ore to finished magnets. Thanks to this, the country has already replaced 80% of its former imports from Asia, and this is just the beginning. It sounds like science fiction, but it's a fact. 2 pounds of cerium can become material for optical lenses of laser systems in military equipment. Other elements, like neodymium, are used in powerful magnets of jet engines and in missile guidance systems. All this means that every ton of ore from Mountain Pass isn't just raw material. It's a piece of American defense independence. The California desert isn't just scorched by the sun, it's politically charged. Mountain Pass is a symbol of a new era where technology and geopolitics merge. Today, American engineers, in hard hats and safety glasses, are literally building their own supply chain of the future, step by step displacing the Chinese monopoly. Just as in the 60s, when the United States first launched a satellite, now they're trying to be first to build an independent rare earth elements industry. And it all starts right here, among the sands, where it was once quiet, but now machines rumble, and the fire of smelting furnaces glows. If you gather all the rare earth elements mined here per year, it's 43,000 tons of concentrate. Outwardly ordinary dust, but actually strategic raw material, more valuable than gold. And if this dust were transformed into finished products, it would power more than 100,000 electric vehicles, those that race without a drop of gasoline thanks to neodymium magnets in motors. The same metals would ensure the operation of hundreds of guidance systems for F-35 fighters, where precision depends on microscopic lasers and sensors. And also, tens of thousands of medical lasers used for eye surgeries or to stop bleeding in military hospitals. The irony is that Mountain Pass isn't a megapolis or a Silicon Valley laboratory, but a patch of land in the middle of the desert. But it's precisely this place that's becoming a PowerPoint again. Every kilogram of cerium mined here is a potential lens for lasers in defense systems. Every gram of neodymium is a piece of an engine for an electric car or satellite. It's worth talking separately about cerium. Cerium isn't just another metal on the list of rare earth elements. It's one of those that sits quietly beneath the surface of technologies, but without it, the modern world would look completely different. Imagine a desert quarry, drilling rigs, machine cries, and dust, and among all this, under sand and stone, hides a complex chemical actor that transforms from an ordinary mineral into a material that affects aircraft, phones, and even medicine. In appearance, an ordinary grayish powder, nothing special. But this is a true alchemist among metals. Without it, there would be no clean glass in telescopes, no shine in smartphones, no precision of lasers, and no cleaner air from automobile exhausts. 1 gram of cerium can do what other materials can't even in hundreds of times larger quantities. Cerium is a true master of transformations. In catalysts, it behaves like a chemical chameleon. It intercepts and releases oxygen, converting harmful gases into harmless ones. In glass, it extinguishes ultraviolet light, makes lenses transparent as crystal. Its oxide polishes phone screens, cameras, optical devices, literally erasing microscopic scratches from surfaces to perfect smoothness. Among workers at the plant, there's a joke. Without cerium, the world wouldn't shine. And there's truth in this. Because when it gets into engineers' hands, everything around starts to shine. Literally. It helps see farther, move faster, burn cleaner, heal more precisely. All this, from desert dust, from a place where heat reaches 110 degrees Fahrenheit, and wind sweeps away traces in a few minutes, as a symbol that even in the driest desert, the future can be born. Mountain Pass was once just a point on the map, the only mine of this type in all of North America. But now it's surrounded by an entire network of structures that transform crude ore into pure elements, ready for the most complex technologies, from electric motors to jet guidance systems. MP Materials Company has built here not just a mine, but a closed-cycle production, something America lost back in the 1990s when all supplies depended on China. After many years of research and investments in hundreds of millions of dollars, new lines operate almost without human participation. All processes are controlled by computers. Sensors measure compound purity, robotic cranes move containers, and special cameras capture every dust particle. Air in laboratories is so sterile that it feels like it's not a desert, but a space station. Everything that comes out of these shops is sent to other factories, which are also being built inside the country. In Texas and Ohio, they're building factories that will manufacture permanent magnets, precisely those that ensure the operation of Tesla electric motors, wind turbines, or fighter guidance systems. Once these magnets were supplied from China almost 100%, but now America plans to completely switch to its own materials by 2030. People who work here say they feel part of something bigger than just production. When they watch as a substance comes out of desert soil that will later turn into part of a satellite or a high-precision laser, it resembles a true miracle. Next to the quarry grow warehouses, laboratories, transport hubs, and on the horizon, also solar panels that power this giant. After the mine closed in 2002, when Chinese companies effectively monopolized the rare earth elements market, only a few dozen workers remained in the Mountain Pass area, maintaining security and basic infrastructure. The nearby settlement declined. Stores closed, roads overgrew with weeds, and local families moved out to look for work. When in 2017, MP Materials Company bought out the assets and launched a modernization program, the situation began to change literally from scratch. Over several years, more than 800 jobs were created at the enterprise itself, not counting hundreds of related ones, in transport, chemical supply, technical service, energy, and even local services. In neighboring towns, cafes reopened, schools received funding, and roads, repairs. Besides direct vacancies, MP Materials launched a professional training program, cooperating with local colleges. Graduates of technical specialties can now do internships right at the modern processing plant, where they learn to work with automated lines, flotators, hydrocyclones, and chemical separation systems. Interestingly, jobs here are very diverse, from geologists, chemical engineers, process operators, to programmers and data analysts who control plant operations through digital panels. Each shift means tens of thousands of parameters read by sensors in real time. In a broader sense, the revival of Mountain Pass has become a symbol of the return of American manufacturing, which for decades was exported abroad. Against the background of political statements about reshoring and strengthening the internal supply chain, this project is often cited as proof that even in the desert, you can create a modern, profitable, and stable industry. Today, I dragged you to a place where the transparent skeleton of our cities is born. Have you ever wondered how an ordinary pile of sand transforms into massive glass panels that hold back the wind on the 100th floor somewhere in downtown Chicago or New York? It's a genuinely cool story about how we learn to tame fire and sand to make things that look fragile but can actually withstand the impact of a small truck. We're at a super-strength glass manufacturing plant, and there's real industrial energy all around us here. Forget about that brittle glass that shatters from an accidental breath. Today we're talking about a material that's the foundation of modern architecture and safety. It all starts with something really simple that you see under your feet at the beach, but with one critical caveat. The main ingredient is quartz sand. But this isn't the sand you wiggle your toes in on vacation. Here it goes through such intensive purification that it becomes purer than your thoughts on the first day after payday. Besides sand, they add soda ash and limestone into this massive steel mixer. Soda ash is needed, so the sand starts melting at a lower temperature, while limestone makes the finished glass resistant to water and chemicals. If we used sand alone, we'd need the energy of a small sun to melt it. But this way, we cheat a little. They also throw in cullet, old chunks of glass that have already served their purpose. This saves a ton of energy and money, because melting an existing structure is way easier than turning stone into liquid from scratch. This entire mix weighs hundreds of thousands of pounds and gets poured into gigantic concrete bunkers, where the big journey begins. Now we're approaching the hottest point of our journey, the furnace. This is a massive structure as tall as a 3-story building that runs non-stop for years. If you shut this furnace down even once, it would simply destroy itself, because the molten mass inside would solidify and tear the walls apart. Inside, it's a real inferno. 2,900 degrees Fahrenheit. It's so hot that if you stood nearby without special mirrored protection, your eyebrows would vanish in a second. Natural gas roars in the burners, creating an incredible noise that vibrates your bones. The mixture of ingredients slowly transforms into a viscous, fiery liquid that looks like super hot honey or lava from a volcano. This liquid slowly flows through a refractory channel to the next stage, one that forever changed the entire industry. This is a bath of tin. That's right, glass literally floats on the surface of molten metal. This process is called the float method. Tin is way denser than glass, so the glass mass spreads across it in a perfect mirror-smooth layer. Just look at this pool 160 feet long, filled with liquid tin. Glass comes out of the furnace and settles onto this metal, becoming perfectly flat through simple gravity. No grinding wheels or expensive polishing. Physics does all the work for us. This is where engineers set the thickness of your future window. Pull the glass faster using special rollers, and it becomes as thin as 1/8 of an inch. Slow it down, and you can get a solid panel a full inch thick that's not so easy to damage. Temperature here gradually drops to 1100 degrees Fahrenheit, and the glass starts to harden, transforming from fiery liquid into an endless ribbon. Next, this ribbon enters an annealing tunnel that engineers call a layer. This is where a critically important process happens. If the glass cools too quickly, internal stresses build up, and it'll literally explode from the slightest touch once it hits the warehouse. So we slowly drop the temperature over several hundred feet of travel. This demands incredible precision, because every single degree matters for the molecular structure. The glass rolls on special steel rollers that have to be perfectly smooth, so they won't leave a single microscopic scratch on the surface, which hasn't fully solidified yet and remains vulnerable. When the glass finally cools down, lasers start checking it. It's basically digital quality control, where machines hunt for microscopic air bubbles or tiny dust particles that might have snuck into the mix back in the furnace. If the system spots even the tiniest flaw, it instantly marks that spot with special paint, and automated cutters just remove the damaged section, sending it back for remelting. The cutters themselves work at incredible speeds. Sharp diamond rollers score perfect lines. Then mechanical arms confidently snap off sheets in the exact sizes needed. But this is just regular glass, the stuff you see in old buildings. We came here for the super strong material that holds up the weight of a skyscraper. To turn glass into a true iron warrior, you've got to temper it. This is my favorite stage, because it's like putting glass through brutal boot camp. A sheet of glass gets heated again to 1200 degrees Fahrenheit, then suddenly blasted with powerful jets of cold air from both sides. This thermal shock creates massive pressure on the glass surface, compressing it, while the center stays in a tensile state. This makes the glass 5 times stronger than regular glass. If you try to hit this stuff with a heavy hammer, it might just bounce right back into your forehead. And here's the best part. When this glass finally does break under incredible pressure, it doesn't shatter into sharp daggers that can slice you up. Instead, it crumbles into thousands of tiny blunt pieces. It's a global safety standard that allows us to use it in modern cars, sports arenas, and massive shopping malls. But if we're talking about skyscrapers in cities that get hurricanes, tempering alone won't cut it. That's when we use lamination. We take 2 separate sheets of glass and glue them together using a special film made of transparent polymer. This technological sandwich gets sent to an autoclave, a massive oven under pressure, where all the air gets sucked out and the film becomes completely transparent, bonding the sheets together at the molecular level. If a brick or even something heavier hits that glass, it'll spiderweb with cracks but stay hanging on that film, without creating a hole all the way through. This is the exact glass that protects people in banks or on observation decks 1,000 feet above the ground. You're standing on a transparent floor, on the 100th story, and you know for certain that polymer layer will hold the weight of 10 people without breaking a sweat. At the end of the line, we see finished steel giants being loaded onto specialized trucks. One of these sheets can weigh over 3,000 pounds, which is why people stopped using their own hands to move them a long time ago. Instead, there are powerful vacuum suction cups on cranes that grip the glass with a death grip. It's a spectacle that makes your heart beat faster. A massive, seemingly fragile panel gliding smoothly through the air, destined to become part of a new architectural structure in just a few days. The entire journey from a pile of sand to this moment took only a few hours of intense work, but packed into those hours are decades of complex scientific research and billions of dollars of investment in technology. When you see skyscrapers glistening in the sun, remember, this isn't just architecture. This is frozen fire. Molten metal and sand that went through temperatures of 5,000 degrees Fahrenheit to become transparent. Glass panels withstand wind pressure of hundreds of pounds per square foot. They don't fear snow, hail, or scorching sun. This is the material of the future, getting stronger and smarter every single year. Maybe soon we'll be building entire cities from it. Cities that are completely transparent, yet tougher than the concrete boxes of the last century. We're standing at a modern asphalt plant. It smells like hot tar, heated stone, and a little bit of my morning coffee, which I nearly spilled when I saw the scale of this metal structure. Most people think asphalt is just some black goop they smear on the road, but it's actually a whole science where every pound and every degree matters. We're about to break down this process into parts and see how a pile of rocks and a barrel of sticky liquid turns into a perfectly smooth highway. It all starts at the aggregate storage yard. These are massive mountains of crushed stone and sand you see behind me. This is serious business. The rocks are sorted by size. We've got really fine screenings, and we've got fractions half an inch or even 3/4 of an inch. Why does this matter, you ask? Because asphalt is like a cake. If you put in too many big nuts and not enough flour, it'll just fall apart under your car's wheels. A special loader grabs this crushed stone and dumps it into huge steel bins. Each container holds about 10 or 15 tons of material. Then begins a long journey on a conveyor belt. This rubber track stretches for dozens of feet and carries the stone to the heart of the plant, the dryer drum. Look at this giant metal tube slowly rotating. It's about 30 or 40 feet long. Inside it, a real flame roars. Why do we roast stone? Because there can't be a single drop of moisture in it. If water gets into the hot mix, it'll turn to steam and punch holes in your future asphalt, what we call voids. The temperature inside this drum climbs to 300 or even 350 degrees Fahrenheit. That's way hotter than your oven when you're baking pizza. Once the stone is properly roasted, it becomes super hot and bone dry. Now it needs to be lifted to the very top of the plant. They use an elevator for this, a vertical chain with buckets that stretches up 60 or 70 feet. Up there at the top, the scorching aggregate gets screened again through a set of sieves. It's like a final quality check to make sure no random wrong-sized rock messes up our road. Now we get to the star ingredient, bitumen. That's the same black sticky stuff that holds all the stone together. It's stored in massive vertical tanks that are constantly heated. If the bitumen cools down, it becomes hard as a rock, and we can't do anything with it. Each of these drums can hold up to 20 or 30,000 gallons of this black liquid. The bitumen is fed into the mixer under high pressure. It looks pretty epic, although peeking inside while it's running is a bad idea, unless you want to become part of the road. The actual mixing process happens in a giant mixer. They dump in a precisely measured amount of hot stone, add mineral powder, think of it like cement dust for thickness, and pour in the liquid bitumen. One mixing cycle takes about 40 or 50 seconds. In that short time, the mixer blades have to coat every single grain of sand with a thin layer of black gold. Imagine the responsibility. If you mix it poorly, the asphalt will start crumbling after the first winter. The finished asphalt comes out of the mixer at around 320 degrees Fahrenheit. It's basically molten black lava. From there, it either gets dumped straight into a dump truck bed, or it heads to a storage silo. These silos look like space rockets sitting on a launch pad. They can hold 200 to 300 tons of hot mix for several hours while maintaining temperature. This lets the plant run non-stop, even when trucks get stuck in traffic jams. I'm standing right now at the control panel. People sit here watching every pound of weight and every degree of heat on their monitors. A modern plant is a fully automated system. The operator just enters the recipe, and the computer decides how much sand, how much aggregate, and how much bitumen to mix. This eliminates human error, because a mistake of 0.1% in the formula can cost millions if the road has to be redone a year later. You've probably heard that asphalt is one of the most recyclable materials in the world, and it's true. This plant has a special unit for adding old asphalt that's been milled off other roads. They grind it up and put it back to work. It's awesome because we're not just tossing old rocks into a landfill, we're giving them a second life. The recycled material can make up 20 or even 30% of the new mix. That's good news for the environment and for the builder's wallet. Let's just take a quick detour right now and peek at how this goes down. Dawn breaks. The highway's blocked off with orange cones, and there's this thick steam rising from the hot asphalt. Feels like we're on the set of a volcano eruption movie. Our dump truck slowly backs up to the paver. This massive iron-tracked machine, worth close to $500,000. The truck bed lifts, and 20 tons of black, steaming mass at 300 degrees Fahrenheit pours straight into the receiving hopper. Inside the paver, powerful augers are at work. Giant screws, just like the one in your meat grinder at home, only 12 feet long. They spread the hot mix evenly across the entire width of the lane. Behind the machine comes the screed plate, which doesn't just level the asphalt. It vibrates with crazy force to compact it initially. The machine leaves behind a perfectly smooth, black-as-night carpet, but it's still too soft. Step on it now, and your shoe stays there forever. And that's when the heavyweights enter the scene. The rollers. First comes the vibratory roller, weighing about 10 or 12 tons. Its steel drums rotate while simultaneously pounding the road at a rate of 40 or 50 strikes per second. You feel this vibration even through the soles of your sneakers from 30 feet away. This is necessary to squeeze out all the air and make the pavement solid. Behind it rolls a pneumatic tire roller on rubber wheels. It smooths the surface, sealing the tiniest pores so water can't get in. One pass after another, and we get a road that'll last 15 or 20 years. Let's go back to the plant. Another interesting point is air cleaning. You see that big box next to the drying drum? That's a baghouse filter. Inside it are hundreds of long fabric bags that capture dust. Only clean water vapor goes into the air, and all the dust is collected and goes back into the asphalt. So stories about these plants being super dirty, that's ancient history. Modern production is cleaner than the kitchen in most fast food restaurants. Now about volumes. A mid-sized plant like this can put out around 240 tons of asphalt per hour. Just to put this in perspective, that's roughly 12 big rigs worth of material. In a single 10-hour shift, this metal giant produces enough asphalt to lay several miles of new 2-lane highway. That's insane speed and massive responsibility. When a dump truck pulls up under the hopper, about 20 tons of smoking black mass pours onto it. Then the driver covers the bed with a special top so the asphalt doesn't cool down on its way to the paving site. If the temperature drops below 250 degrees Fahrenheit before it gets rolled out, you won't get a quality road. So logistics here is a real race against time. Watching one of these plants operate is like watching a really big, really complicated food processor. Nothing here is wasted. Every motor and every sensor performs its exact function. And while from the outside it looks like a pile of smoking, rumbling metal, it's actually a triumph of precision and engineering calculation. Every mile of highway we drive on vacation or to work started right here, in this hot, noisy place. Stick with me. We've got plenty more fascinating machinery and weird mechanisms coming up that make our lives more comfortable, even if we usually don't notice them. This single tank holds an entire Olympic pool's worth of fuel. Hard to believe. Look at this, 10,000 gallons in each one of these tankers. I'm standing here in a massive, towering factory right in the heart of America, where these steel giants are born from scratch. This isn't just a workshop, it's a true industrial cathedral, where instead of organ music, you hear the roar of metal, and instead of incense, you smell ozone and white-hot steel. Today, we're diving into the process of building a fuel tanker, those same shiny cigar-shaped missiles that race down highways, loaded with gasoline or diesel. I've already walked these floors, talked to workers whose faces are hardened by heat and labor, and now I'm going to tell you everything. To do that, you need to follow me. Don't fall behind. Ready? Then let's roll. This is going to be incredibly fascinating. First comes the raw material, the lifeblood of a future giant. It all starts not with ore, but with perfectly flat, thick steel sheets arriving on railroad platforms. Picture a sheet of metal 25 feet long and 10 feet wide. It's like a small billboard, only made of steel. And this steel isn't ordinary. It's a special alloyed blend containing chromium for rust resistance and molybdenum for incredible strength. It's engineered to withstand insane pressure, impacts, and constant corrosive attack from fuel. Each of these sheets weighs 3 tons. Workers in bright hard hats, like ants around a giant treasure, use overhead cranes gliding smoothly beneath the ceiling to lift these sheets and carefully stack them. Everything's computer controlled, with laser scanners checking every millimeter of surface for detected defects, microcracks, or irregularities. Only perfect raw material gets the green light to move forward. Now it's time to cut the metal. Sheets roll from the warehouse onto the cutting table. A portal looms over the sheet, and a cutting head hisses along its track. This is a giant plasma cutter. From the nozzle, under massive pressure, erupts a jet of gas heated to tens of thousands of degrees Fahrenheit. It's like a tamed lightning bolt. That jet slices into the metal like butter. Sparks fly in every direction. Like fireworks, the air hums with power, and the smell of ozone fills the shop. A computer program guides the cutter along a perfectly calculated path, carving 2 or 3 panels for the future tank from a single sheet with accuracy down to a 1/4 inch. Each panel has all the necessary openings for future valves and hatches. After cutting, the panels are still hot and a bit rough around the edges. Next up, bending the panels, giving them shape. That's where the real heavyweights come in. 200-ton hydraulic presses. Picture a giant machine that slowly, but with unstoppable force, bends thick steel plate like it's a sheet of paper. A crane feeds in a flat panel, and the machine, pressing it against a massive curved die, transforms it into a perfect arc. That's how the cylindrical sections of the tank and the rounded ends are born. The cylindrical body gets assembled from several of these sections and ends up 50 feet long and 10 feet in diameter. After each bend, workers check angles and radii using special templates and tape measures. Everything has to be perfectly round. Why? Because in a circular vessel, pressure distributes evenly. Any warping, any flat spot, that's a stress point where, under fuel pressure, the tank could rupture. Fuel doesn't tolerate compromises. Welding, that's where the heart of the process is, where separate pieces become one whole. This is where real craftsmanship lives. Welders in masks with automatic ultraviolet filters aren't just handling simple equipment, they're operating automated submerged arc welding systems. That means the welding robot runs along the entire seam, and the arc itself burns not in open air, but beneath a thick layer of special flux powder. This creates a perfectly clean, deep weld, 1/2 inch thick, that's actually stronger than the metal itself. After welding, our tank is one piece, but it's stressed out. Welding creates internal tensions in the metal that need to be relieved, so it's heading for heat treatment. A giant crane carefully lowers the entire 50-foot tank into a massive furnace. The doors close, and the temperature inside slowly climbs to 1,600 degrees Fahrenheit. It rests in that oven for about an hour. This process makes the metal more elastic and releases all the stress. Then the doors open, and out comes a red-hot monster, steam pouring off it. Workers in silver suits start hosing it down with water for controlled cooling. The air fills with a loud hiss, like 1,000 kebabs hitting the grill at once. I laughed and told the guys, "This is your sauna." Now for painting and coating. The cooled tank gets sent to a paint facility. This thing's the size of an aircraft hangar. Then comes the first layer, an epoxy primer that protects against rust. After that, 2 coats of top coat, white for better visibility on the road, and silver with added aluminum powder to reflect sunlight so the contents inside don't heat up. But what's on the inside? That gets special protective coatings. A thin but incredibly tough layer of polyurethane, just 10 millimeters thick. It's completely inert, doesn't react with fuel, and won't crack from vibrations. Workers use laser thickness gauges to check every square inch. No gaps allowed. Installing the fittings is the final touch that transforms the barrel into a high-tech tool. They mount the valves: fill valve on top, drain valve on the bottom, plus an emergency valve to release excess pressure. Each valve is a work of art made from stainless steel, rated for 200 pounds per square inch. They install electronic sensors for fuel level, temperature, and pressure. All the data feeds to a computer in the driver's cab. They mount an inspection hatch, 2 feet in diameter, with hermetic seals. I climbed inside an empty tanker myself, space like a space capsule, and absolute silence, because the 1/4-inch thick walls perfectly dampen sound. Testing, the most exciting and critical stage. First up, hydraulics. They fill the tank completely with water and pressurize it to 250 pounds per square inch. Inspectors with flashlights walk around it for 2 hours, hunting for even a single drop. If there's nothing, the tank is sealed tight. Next, the vacuum test. They pump out the air and check if the pressure drops. And the final, most precise test, pneumatics with helium. They fill the tank with pressurized helium, and special sniffer sensors check for the tiniest leaks. If not even a microscopic helium atom seeps through, the tank is ready for fuel. I watched them fill one test tank with 10,000 gallons of gasoline. Not a whiff of smell outside. The final stage, inspection and marking. A special plate gets stamped with a serial number, manufacturing date, and the empty tank's weight, 20,000 pounds. They slap on Department of Transportation certificates with all the safety specs. And then, a giant crane carefully lifts the finished gleaming tank and mounts it onto the truck chassis. Now it's ready to roll down the highway. Guys, this factory only produces 2 of these tanks per month. Each one's like a little mobile fuel fortress, incredibly safe and reliable. I'm absolutely blown away. From a simple steel sheet to a finished tank, every single detail is thought through. If you see these tankers on the road, know there's incredible work behind them. Thanks for watching. Hit that like button, subscribe, and I'll see you on the next factory tour. What if I told you there's a metal that can't be destroyed by fire, pressure, or time? A material without which aviation would stop, lights would go dark, and space engines would fall silent. And yet, it's so rare that the entire world fights over every single gram. But here's the real kicker. By the end of this video, you'll learn a secret about tungsten that the industry hides and almost nobody talks about. Something that'll flip your understanding of the metal holding civilization together. Tungsten is a true engineering phenomenon. Its unique properties let us push the boundaries of what's possible in technology, from deep underground to the heights of space. Its story, a story of endurance and unmatched strength. Tungsten is element 74 on the periodic table, one of the transition metals. It has the highest melting point of any metal on Earth, a staggering 6,192 degrees Fahrenheit. To put that in perspective, that's a temperature where most other metals would have vaporized long ago. On top of that, tungsten has the highest tensile strength of any pure metal, at temperatures above 3,000 degrees Fahrenheit. It's incredibly hard and dense, making it irreplaceable for applications demanding maximum resistance to wear, deformation, and extreme temperatures. Tungsten doesn't occur in pure form. It's extracted from ores, with the most common being wolframite and scheelite. Wolframite is a complex compound of iron, manganese, and tungsten, while scheelite is calcium tungstate. These ores, hidden deep in the Earth's crust, are the raw material for all subsequent industrial processing. The world's major tungsten producers include countries like Vietnam, China, Russia, and Canada, which hold significant reserves of this strategic metal. The tungsten extraction process is a complex sequence of mining and metallurgical operations. It starts with exploration and ore extraction from underground mines or open-pit quarries. Geologists use various methods to identify and assess tungsten ore deposits. Then, using powerful drilling rigs and explosives, the ore is extracted from deep within the earth. It's tough, dangerous work that demands cutting-edge technology and strict safety standards. Thousands of tons of ore are hauled to the surface every single day. After extraction, the ore heads to a processing plant. Here it goes through several stages to separate valuable wolframite or scheelite from other rock. First, the ore gets crushed in crushers and mills until it's a fine powder. Then various enrichment methods kick in: gravity separation, magnetic separation, and flotation. These processes yield a concentrate containing 60 to 70% tungsten trioxide, which is an intermediate form. The concentrate is then processed at metallurgical plants to extract pure tungsten. It's a complex chemical process that can involve alkaline leaching, precipitation of ammonium paratungstate, and its subsequent roasting to produce tungsten oxide. The tungsten oxide is then reduced to metallic tungsten by heating it in a hydrogen atmosphere at temperatures ranging from 2000 to 3300 degrees Fahrenheit. The result is a fine tungsten powder, which forms the foundation for all subsequent products. From this powder, through sintering, tungsten rods, bars, and other blanks are formed. Tungsten powder is pressed under high pressure into the desired shape, then sintered at extremely high temperatures in a hydrogen atmosphere. This allows the powder particles to bond together, creating a dense, strong material. One of the most critical applications: manufacturing tungsten carbide. Some seriously tough stuff. These alloys combine tungsten with carbon, plus cobalt or nickel as a binder, creating one of the hardest man-made materials on Earth. They're used to make cutting tools, drill bits, end mills, lathe inserts that can slice through the hardest metals and alloys. Without tungsten carbides, modern manufacturing, metalworking, and oil and gas extraction would grind to a halt. A single pound of tungsten can become a drill bit capable of boring through thousands of feet of rock. Talk about efficiency. Tungsten also sees heavy use in military applications for armor-piercing rounds and bullet cores. Thanks to its extreme density and hardness, tungsten alloys have exceptional penetration characteristics, delivering devastating effectiveness against armor. It's also used in heavy armor plating and counterweights. In electronics and electrical engineering, tungsten is indispensable. It's used to make filaments in incandescent bulbs, welding electrodes, electrical contacts, and other components that need high heat resistance and electrical conductivity. Because of its sky-high melting point, it's used in the aerospace industry for parts exposed to extreme temperatures. High-temperature tungsten alloys are used in jet engines, turbines, and other devices operating under extreme heat. Alloying with tungsten boosts the heat resistance of other metals. In medicine, tungsten is used in manufacturing X-ray tubes thanks to its high atomic number, which effectively blocks X-rays. It's also used in radiation shielding, similar to lead, but with way less toxicity. On top of that, tungsten's used to make ballasts and counterweights in race cars, aircraft, and yachts thanks to its crazy high density. It's even a component in some jewelry because of how hard it is and how resistant to scratches. Tungsten is one of the rarest elements in Earth's crust, which makes mining and producing it especially valuable. Global tungsten reserves that are economically viable to mine are estimated at roughly 3 to 3.5 million tons. However, when you factor in potential resources that haven't been explored yet, the total volume could be significantly higher. That's obviously way less than reserves of metals like iron or aluminum, which really highlights its strategic value. Global tungsten production each year, measured in tons of pure metal or tungsten oxide equivalent, fluctuates, but in recent years, it's been somewhere between 85,000 and 100,000 metric tons annually. This figure includes both primary extraction from ores and recycling, which is becoming increasingly important. Imagine this. You could take a worn-out tool that's already served its purpose and transform it back into something brand new, without spending the energy and resources to mine ore from scratch. That's exactly what happens with tungsten. Tungsten recycling is one of the most advanced and efficient processes among all metals. By various estimates, up to 40% of all tungsten consumed worldwide comes from recycled material. That's a massive number. It shows just how valuable this metal is and how much economic sense it makes. Where does used tungsten come from? The main source of secondary raw material for tungsten is, of course, worn-out carbide tools. Those same cutting tools, drill bits, milling cutters made from tungsten carbide. After heavy use, they wear down, lose their edge, or break. Instead of tossing them in the trash, they're collected and sent to recycling plants. Other sources include scrap metal containing tungsten, leftover waste from tungsten product manufacturing, plus some electrical contacts and wires. Recycled tungsten is significantly cheaper to produce than primary metal because it eliminates the expensive and energy-intensive stages of mining ore and initial processing. Recycling dramatically reduces the environmental footprint of tungsten production. It minimizes the need for mining operations, cuts energy consumption, reduces industrial waste, and lowers greenhouse gas emissions. This makes production more green and responsible. Can metal burn brighter than the sun? Sounds impossible. But one element does this every day, and we're about to touch its mystery right now. Imagine a material lighter than plastic, yet capable of withstanding loads that break steel. A material hidden in seawater, in stone, in the technology around us, but the way it's extracted looks more like alchemy than industry. And here's the thing. By the end of this video, you'll learn about a property of magnesium that even many engineers have never heard of. Ready to discover what giant furnaces, seawater, and 1,000-degree flames have been hiding? Magnesium is often called the metal that defies intuition. It's lighter than many types of plastic, weighing approximately 0.063 pounds per cubic inch, 1.5 times lighter than aluminum, and nearly 4 times lighter than steel. In your hands, it feels almost hollow inside, yet this metal demonstrates remarkable strength in alloys and can withstand loads its mass simply doesn't suggest. What's most striking is how it burns. Given sufficient temperature, magnesium produces light so intense that its brightness reaches close to 3,500 degrees Fahrenheit, and watching the flame without protection is impossible. That's precisely why magnesium flashes were once used in photography and pyrotechnics. During combustion, it forms white smoke of magnesium oxide, and the flame itself looks as if someone turned on a concentrated beam of sunlight. In nature, pure magnesium doesn't exist. It's bound up in minerals, and the two main sources are dolomite and seawater. Global estimates suggest that the oceans contain over 1.3 quadrillion tons of magnesium, making it one of the most abundant metals in a form accessible to humanity. However, extracting it from water is a complex and energy-intensive process. Picture an industrial facility on the coast where the sea is essentially raw material. Everything runs continuously through a system of powerful pumps. Pipelines stretch from the shore to the processing units, moving thousands of gallons per hour. The water flows into large open or enclosed basins resembling giant reservoirs, where it's filtered for the first time to remove debris, sand, and biological contaminants. After that, in similar tanks, a calcium hydroxide slurry is added. This happens through automated dispensers that feed the material into the water, so the reaction proceeds evenly. From the outside, it looks like a slow transformation of transparent seawater into a cloudy liquid, as if someone added fine white powder that gradually binds the dissolved magnesium into flakes of sediment. While the reaction continues, large mixers move through the pool, sometimes resembling windmill blades, only turned horizontally. They stir the liquid almost silently, so the sediment forms everywhere rather than clumping together in one spot. When the particles become heavier and start settling to the bottom, the liquid is pumped into the next settling tank. There it sits for several hours, and the solid fraction slowly settles, forming a dense layer that looks like wet cement. The upper part of the water is drained back into the sea or directed for retreatment, while the sediment is collected by special grabs or vacuum systems. Then, the sediment is rinsed with fresh water and dried in powerful drying ovens that blow hot air at speeds capable of removing an entire layer of moisture in a minute. When the mass becomes brittle, it's moved to roasting furnaces. Inside, temperatures exceed 1,380 degrees Fahrenheit, and the material gradually transforms into magnesium oxide. From the outside, it looks like an endless white ribbon of powder, being fed by conveyor into the scorching chambers and emerging with a completely different structure. The final stage is electrolysis. The oxide enters sealed high-temperature chambers where it's mixed with salt flux. This happens either in smelting vats or in special crucibles, where the material gradually transforms into a thick, molten mass. The metal chamber walls glow red from the heat, and inside, the molten material looks like incredibly thick, scorching soup. At this point, electric current passes through it. You can only watch through protective windows, because everything inside appears to glow. Magnesium begins separating into tiny droplets that rise to the surface, since their density is lower than the molten mixture. It's collected using special ladles or drainage systems, and eventually the metal accumulates as shiny silver ingots, ready for further purification or casting into molds. In the case of dolomite, everything starts at the quarry, where the rock lies in massive layers. Extraction doesn't look like romantic stone chipping. It's the work of giant excavators, drilling machines, and blasting equipment. First, the rock gets crushed right on site. Massive jaw crushers chew through refrigerator-sized chunks and turn them into material that can move along conveyor belts. From there, the dolomite heads to factory hoppers, where machines precisely meter the flow and feed it into calcination kilns. The kilns work like giant tubes heated to 1650 degrees. Inside, the dolomite slowly descends, while hot air, fed from below, passes through the entire layer of material. From the outside, you only see bright bands of glowing metal, but inside, something crucial happens. The dolomite breaks down into magnesium oxide and calcium oxide. After leaving the kiln, the hot mass travels along metal chutes and cools under powerful blasts of air. Next comes the stage where dolomite transforms into something resembling factory architecture. A tall tower with vessels, pipes, and tanks. Coke, or ferrosilicon, is fed into this tower, along with pre-crushed calcined dolomite. This mixing happens in specialized reactors that look like enormous drums, slowly rotating to ensure uniform contact between reagents. Everything appears as a continuous flow of dry, grayish powder sliding into the reduction furnace. Inside the furnace, the temperature climbs even higher, over 2,550 degrees. The heat inside is so intense that everything around glows with a dim red light. Under these conditions, magnesium oxide reacts with the reducing agent, and the metal transitions into vapor phase. This is one of the most distinctive features of magnesium production. The metal evaporates and rises through the furnace, while gaseous particles move into the condensation chamber. The chamber looks like a vertical steel cylinder with cooled walls from the outside. Inside, magnesium vapors meet the cold surface, and the metal condenses as a shiny coating that resembles silvery frost. This coating gets periodically scraped off by mechanical scrapers or robotic manipulators operating in an environment with minimal oxygen access. The collected metal goes into protected containers, where it's melted again to remove residual impurities. The melting crucibles look like deep wells filled with glowing silvery molten metal, and extraction systems constantly work above them, protecting the metal from contact with air. The process ends with casting into molds, where magnesium cools and transforms into ingots. Each ingot represents the end of a long journey, from stone extracted by explosions to metal that emerged through evaporation and condensation. Global magnesium production holds steady at around 1 million tons per year. China supplies roughly 85% of that volume, while the United States, Israel, and Kazakhstan handle the rest. Interest in the metal grows annually because the aerospace, automotive, and electronics industries are hunting for the lightest materials possible. For example, using magnesium alloys in transportation cuts component weight by 20 to 35% compared to aluminum. That reduces fuel consumption and boosts overall efficiency. In electronics, magnesium shows up in laptop casings, camera bodies, and smartphones. It's not just light, it also absorbs vibrations well and dissipates heat effectively. In the United States, the share of magnesium in automotive parts has climbed from 3 pounds per vehicle 20 years ago to over 12 pounds in current models, and that figure keeps rising. Despite magnesium being lightweight, flammable, and extremely reactive, it's incredibly difficult to replace. It has a rare combination of mass, strength, and reactive properties that make it one of the most important structural metals of our time. And even though humanity has been producing it for only a century, the potential for its use hasn't come close to being exhausted. If current trends in aviation and electric vehicles continue, analysts predict global demand will reach 2 million tons within a decade. Every year, humanity mines nearly 2.5 billion tons of iron ore worldwide. That's over 5 trillion pounds of metal, without which we wouldn't have skyscrapers, roads, or even your smartphone. Iron drives civilization, but few people know where it truly comes from. Because every piece of this metal isn't just ore from a quarry, it's actually a fragment of an ancient star's explosion. And today, you're going to learn something most people don't even suspect. Stick around till the end. There's a hidden answer there that will completely change how you think about iron. The global iron production is an incredibly massive process that drives industrial development and shapes the modern world. Every year, the world extracts nearly 2.5 billion tons of iron ore, or more than 5 trillion pounds. This ore is the primary raw material for steel, without which we couldn't imagine building skyscrapers, cars, bridges, or even modern machinery. The leading iron ore producers are China, Australia, and Brazil. Australia, for example, mines more than 900 million tons per year, which is roughly 2 trillion pounds, making it the world's largest ore exporter. China, while producing significant amounts of its own ore, is also its biggest consumer, using nearly 1,200 million tons annually for steel production. Iron ore mining involves massive quarries where giant trucks haul hundreds of tons of ore in a single trip. For example, one modern Australian mining truck can carry over 400 tons of ore at once. That's equivalent to the weight of more than 270 average cars. The global iron industry keeps pushing forward. Thanks to innovations in extraction technology and reduced energy consumption, production is becoming more efficient and environmentally friendly. Take the United States, for instance. They're implementing new systems to cut carbon emissions in steelmaking, gradually transforming traditional approaches to the industry. Iron demand is skyrocketing worldwide, especially in developing nations where they're building roads, railways, and massive infrastructure projects at breakneck speed. Simply put, iron is the real engine driving global development, and its production is a powerful indicator of economic strength. The iron we pull from the Earth's crust has cosmic origins. It was formed in the distant past, long before our planet even existed. Most of the iron in the universe was born in the hearts of ancient stars through processes called nuclear fusion. When a massive star reached the end of its life cycle, it exploded as a supernova, blasting heavy elements, including iron, out into space. This cosmic dust and gas gradually came together over time, forming molecular clouds that eventually compressed into protoplanetary disks. Earth's iron is what remains of these ancient stellar explosions, preserved and woven into the very fabric of our planet. That's why iron is one of the most abundant metals on Earth. During Earth's formation, over 4.5 billion years ago, the early planet was molten due to intense gravitational compression and frequent meteorite impacts. During this period, heavier elements, including iron, sank towards the center, forming the planet's core. Today, it makes up roughly 1/3 of Earth's total mass, and that's exactly why our planet has its unique magnetic field. The iron core powers this protective shield. Iron in the upper layers of the planet forms mainly as iron ore, a mixture containing oxides and other iron compounds. It's distributed throughout Earth's crust and mantle, and that's where we extract it from to create metal for every aspect of our lives. From iron's origins in stars to its crucial role in shaping our planet, this metal has traveled an incredible journey before becoming part of buildings, machines, and even your smartphone. So every piece of iron in the world is essentially a cosmic artifact, carrying within it the history of the universe and our planet's shared story. Iron almost never occurs in pure form in Earth's crust. It's hidden within numerous minerals, oxides, sulfides, silicates, carbonates, and other compounds. The most common iron minerals are hematite, magnetite, siderite, limonite, and pyrite. The iron content in these ores ranges from 10 to 70% or more, depending on the type and quality of the ore. To get metallic iron, you need a pretty aggressive and complex technological approach. In industry, the main method is the blast furnace process, where iron ore gets heated in a blast furnace at extremely high temperatures, around 2,900 degrees Fahrenheit. There, under the action of coal and other additives, the ore is reduced, meaning oxygen is separated from the iron, and molten metallic iron forms, which collects at the bottom of the furnace. Other methods, like direct reduction of iron, are used to extract metal from finer concentrates in the form of iron powder or sponge iron, which can then be remelted. So, iron gets freed from minerals through engineering processes that demand extreme temperatures and chemical reactions. This aggressive approach is what transforms the iron buried in ores into strong metal, the foundation of modern civilization. The molten metal pools at the bottom of the furnace, separating from the slag, impurities that float to the surface. Pig iron typically contains 3 to 5% carbon and other impurities, so it needs further processing. The next stage is the converter process. Here, molten pig iron from the blast furnace gets transported to an oxygen converter, where a jet of oxygen further oxidizes excess impurities and carbon. The result is steel with controlled carbon content, maximum 2%, depending on the steel grade. The molten steel then moves to the casting lines. This is where slabs are formed, massive flat ingots ranging from about 6 to 12 inches thick and up to several feet wide. A single slab can weigh dozens of tons. These slabs are an intermediate product that's then sent to rolling mills, where they're transformed into flat sheets, strips, or other profiles for future use in manufacturing structures, automobiles, construction rebar, and many other products. It's important to note that this entire technological chain requires high energy intensity and precise control of parameters, temperature, chemical composition, and processing time. Engineers control the process with high precision to achieve the necessary steel quality, strength, and durability. Besides traditional blast furnace production and converter refining, modern metallurgy increasingly uses electric arc furnaces, where steel scrap is remelted with molten iron, added to save resources and reduce environmental impact. The process starts with loading steel scrap into the furnace, pieces of metal, production waste, or old metal products. To improve steel quality and optimize melting, iron particles or iron concentrates are sometimes added to the scrap metal. After loading, the electrodes lower until they make contact with or get close to the scrap, and current flows through them. An electric arc forms between the electrodes and the charge, reaching temperatures up to 6,300 degrees Fahrenheit. Heating the charge under the arc's influence causes the scrap metal to melt rapidly. The molten steel forms a pool of liquid metal that mixes intensively thanks to electrodynamic vibrations and natural convection. This ensures uniform heating and metal composition. To purify the molten steel from unwanted impurities, oxygen is introduced into the furnace through special tuyeres. The oxygen oxidizes carbon, sulfur, phosphorus, and other harmful elements, forming slag that's easily removed. Alongside this, fluxes are added, materials that help neutralize impurities, improve slag formation, and protect the metal from air exposure. Refining continues until the desired chemical composition is achieved. When the metal reaches the required quality and temperature, It's poured from the electric arc furnace into special ladles, containers for transporting liquid steel to the next processing stages. On continuous casting lines, the molten metal is transformed into slabs. The weight of a single slab can reach anywhere from 20 to 30 tons. These billets serve as the foundation for further rolling into sheets, bars, pipes, and other metal products. The main advantage of electric arc furnaces is that they can run almost entirely on scrap metal, which dramatically cuts down the need for mining iron ore and slashes energy consumption. This makes steel production way more eco-friendly and cost-effective. The furnace is constantly monitored by operators who adjust the current strength, voltage, and oxygen flow to optimize melting and hit the exact steel specs needed. Graphite electrodes wear down over time from the extreme heat and need to be replaced regularly. S. Let me show you something incredible. This is a substance that weighs more than lead, gold, or any other metal on the periodic table. We're in Oregon, at a unique facility where they purify and process osmium. It's the 76th element that most people have never heard of in their lives, and that's a real shame. Osmium is like the introvert of the chemistry world. It's so rare and specific that most people simply don't encounter it in everyday life. This is extreme physics at its finest. Ready to see this cosmic stuff with your own eyes? Then let's go inside. First thing they told me walking in, don't touch anything with bare hands. Not because it's expensive, though it's expensive too, but because osmium in certain forms releases a compound that irritates mucous membranes and in sufficient concentration can damage your retina. It's called osmium tetroxide. So everyone here wears gloves, and the ventilation here is more serious than in a hospital wing. Great way to start a tour, right? But I'm already inside, cameras rolling, and there's no backing out now. Wish me luck. Now for the numbers, because without them, I don't understand why anyone would even mess with this stuff. Osmium melts at 5,486 degrees Fahrenheit. It's the highest density of all known elements. A matchbox with a volume of about 3 cubic inches, if you made it entirely from osmium, would weigh around 12 pounds. 12 pounds. That's like a small bag of groceries, only the size of your palm. I held a sample like that once. The feeling's bizarre. Your brain's telling you something this size can't weigh this much, but your hand's absolutely not buying it. It's one of those moments where the number in the textbook and the actual sensation in your palm are two completely different things. Another number worth keeping in mind, osmium's melting point, 5,521 degrees Fahrenheit. It's the third hardest metal after rhenium and tungsten among refractory elements, way higher than steel, which melts somewhere around 2,000 degrees. In practical terms, you can't melt osmium in an ordinary industrial furnace. Period. That's why they don't make ingots here, and they don't cast parts like at a regular metallurgical plant. The whole process takes a different route. More on that in a bit. Where does osmium come from? You don't find it like iron. No quarries or mines. Osmium's a byproduct of processing nickel and copper ore. Deep in the mines of South Africa or Canada, they're extracting nickel ore, and osmium just happens to be present in trace amounts alongside platinum, palladium, and iridium. Concentration, 1 to 10 parts per billion. To get a single pound of osmium, you need to process 500 to 1,000 tons of raw ore. That's why the market price sits between $1,500 and $2,000 per troy ounce. For comparison, gold currently runs just over $2,000 per troy ounce. Osmium is nearly neck and neck with it price-wise. The raw material arrives at this facility as osmium-bearing concentrate, a grayish-black powder packed in sealed stainless steel containers. The containers are small, about the size of a coffee can. Inside might be 2 to 5 troy ounces of material. Each one of these cans represents $3,000 to $10,000 of raw material. They arrive in a regular courier van, but with paperwork running several pages and cargo insurance. The exact amount isn't disclosed publicly, but from the manager's expression, it's clear the figure is substantial, and a small sample taken for incoming analysis. Literally a few milligrams of powder that go into a spectrometer. If the composition doesn't match the documentation, the batch gets returned. No discussion. First purification stage, dissolution. The concentrate goes into a reactor with an acid mixture at around 350 degrees Fahrenheit. Osmium converts to gaseous tetroxide during this process, the very compound they warned me about at the entrance. This gas is immediately captured and absorbed by a specialized solution in a sealed tube system. Zero external leakage. The system gets checked for integrity every morning before startup. Next, chemical reactions convert the osmium back into solid form and store it as what's called osmium sponge, a porous dark powder containing approximately 95% metal. This whole process takes 6 to 10 hours per batch, and there's no rushing it. The reaction proceeds at its own pace, and nobody tries to speed it up. The second stage is hydrogen reduction. The osmium sponge gets placed in a tube furnace, through which hydrogen is passed at a temperature of 1100 degrees Fahrenheit. The hydrogen picks up residual oxygen impurities, and what comes out is metal powder with a purity of 99.9%. This takes another 4 to 6 hours. The tube furnace looks completely ordinary, a metal tube about 3 feet long, hooked up to a gas line. If you didn't know what was happening inside, you'd think someone was just drying laundry. But inside this tube, the powder transforms from a dirty concentrate into one of the purest metals produced commercially in the United States. Stage 3 is pressing and sintering. The powder gets loaded into a steel die and pressed at roughly 3,000 pounds per square inch. You get a small cylinder, about an inch in diameter and half an inch tall. Looks like a coin, only thicker and darker. Then this cylinder goes into a separate furnace, this time at 2000 degrees Fahrenheit, where the powder particles fuse together into a solid metal. After sintering, the density of the sample is already 22.5 grams per cubic centimeter, very close to the theoretical maximum for this metal. Shrinkage during sintering runs about 15% of the original volume, and you've got to factor that into your calculations ahead of time, because the die has to be created with extra room for exactly that shrinkage. After sintering, each sample is weighed and measured. Weighing here isn't just a formality. The scales are accurate to 1,000th of a gram, because at these metal prices, losing even a few hundredths of a troy ounce is real money. All trimmings, all leftover powder, all fine dust from under the press, collected and returned to the recycling loop. Nothing gets thrown away. Even the wipes used to clean work surfaces go to regeneration. They might contain a few micrograms of metal too. Where does finished osmium go? One application, nibs for premium fountain pens. Osmium is incredibly hard and wear-resistant, so a pen like this can write for decades without noticeable tip wear. That's why you'll see Oz marked on expensive pens next to the manufacturer's name. Another application, electrical contacts in relays and measuring instruments, where you need longevity through millions of cycles, and where ordinary copper or silver wears out faster. And the third area, one they talk about more carefully here, medical implants. Osmium combined with iridium creates an alloy of exceptional hardness, used to make pacemaker components and certain orthopedic devices. The human body barely reacts to this alloy. It's biologically neutral, which in medicine is extremely expensive in the most literal sense. The details of contracts with medical manufacturers, those aren't disclosed here. I asked how much finished metal they produce per month. The answer, 20 to 50 troy ounces. That's 4 to 10 pounds of metal over 30 days of operation. Sounds ridiculously small. But in terms of value, $30,000 to $100,000 monthly from a single facility of this size. And there's a backlog of orders 3 to 4 months out. Demand is steady, supply is limited by nature itself. There won't be more ore, and the number of facilities worldwide that actually know how to handle this metal properly, you can count them on one hand. What do you think will happen when osmium runs out? Drop a comment, because I can't stop thinking about it. But your hand feels something fundamentally different from anything I've held before. Your brain refuses to believe it, but physics doesn't ask permission. That's the whole difference between knowing the number and feeling it in your palm. 12 pounds in your fist and 0 special effects. A pinch of metal, a few hundred grams per ton of steel. Add it, and the steel gets 30% stronger. Same weight, same thickness. But it takes a third more force to break it. That pipeline under the North Sea, the one carrying gas at thousands of pounds per square inch? Without this metal, the walls would need to be twice as thick. The project, twice as expensive. Nearly 90% of this metal comes from one country, Brazil, and most of it from one single mine.